Close your eyes for a moment and imagine the night sky. It feels still, doesn't it? The stars seem fixed, like tiny holes in a dark ceiling, quiet, unmoving, almost permanent. For most of human history, that's exactly what people believed, that the universe was like a giant painting, beautiful, but frozen in place. But that picture isn't real. Everything you see up there is moving, not slowly, not gently, but at speeds so fast they are almost impossible to imagine. And the strange part is, we don't feel any of it. So how did we discover this? It began with a simple question. What if the stars aren't standing still? At first, people noticed something small. Certain stars seem to shift ever so slightly over long periods of time. Not enough to notice in a single night, but enough that careful observers, watching over years, could tell something was changing. Then came better tools, telescopes became stronger, observations became more precise, and slowly, a quiet realization began to form. Those tiny points of light were not fixed. They were drifting. At first, this didn't seem too shocking. After all, things move, planets move, the moon moves, even Earth moves around the sun. But then the scale of the discovery began to grow. Those stars in the distance, many of them weren't just stars. They were entire galaxies, massive collections of billions of stars, all grouped together like glowing cities in the dark. And they weren't just sitting there, they were moving too. Now here's where things get interesting. You might expect that if everything is moving, it would look chaotic, like a swarm of bees flying in every direction. And at first it did seem that way. Some galaxies appeared to move away from us. Others seemed to move across our line of sight. Some even moved toward us. So people naturally thought, okay, everything is just drifting randomly. But that wasn't the full story. As measurements improved, patterns began to appear. Subtle at first, but undeniable. It was like looking at leaves floating on a river. If you focus on just one leaf, it might spin, wobble, or drift in odd directions. It feels random. But if you zoom out, you start to see the current, the flow, and suddenly, all those small movements make sense. The same thing was happening in space. Galaxies weren't just moving randomly. They were part of something bigger, a kind of cosmic flow. But before we go there, let's pause for a second and ask something simple. If everything is moving, why don't we feel it? Think about being inside an airplane. When the plane is cruising smoothly, you don't feel like you're moving at all. You can sit, relax, even fall asleep. It feels like you're completely still, but in reality, you're moving at around 800 kilometers per hour. That's fast enough to travel from one city to another in less than an hour. The reason you don't feel it is because everything around you is moving with you. The air, the seats, your body, all part of the same motion. Now take that idea and stretch it to a cosmic scale. We are inside a moving system. Earth spins on its axis. Earth orbits the sun moves through the Milky Way, and the Milky Way itself moves through space. All of this is happening at the same time, so we don't feel it, because we are part of it. It's like being carried by a current you can't see. Now here's a question that might come to mind. How fast are these galaxies actually moving? The answer is unbelievably fast. Some galaxies move at speeds of hundreds of thousands of kilometers per hour. To picture that, imagine driving a car at highway speed, let's say 100 kilometers per hour. Now multiply that speed thousands of times. That's the kind of motion we're talking about. And yet, from where we are, they look completely still. This is one of the strangest things about the universe. Something can be moving incredibly fast, and still look frozen. Why? Because of distance. When something is very far away, even large movements become hard to see. Think of an airplane high in the sky. From the ground, it looks like it's barely moving, slow, almost hovering. But inside that plane, everything is rushing forward at incredible speed. The same illusion happens with galaxies. They are so far away that their motion becomes subtle, almost invisible. But with careful measurement, we can detect it. And once we do, the stillness disappears. The universe begins to feel alive, dynamic, restless. Now, there's another important idea here that many people misunderstand. Some people think that space itself is empty and calm, like a quiet void where things just float. But that's not quite true. Space is more like an ocean, and galaxies are like boats, or even leaves, drifting along currents we don't fully see yet. Sometimes they move closer together, sometimes they drift apart, sometimes they follow paths shaped by forces we can't directly observe. And this leads to a deeper question. If everything is moving, what is guiding that motion? Is it random, or is there something pulling everything in a certain direction? This question didn't have a clear answer at first, but as more data came in, the picture became clearer. The motion wasn't random. There were patterns, large-scale patterns, entire groups of galaxies moving together, like schools of fish in a vast cosmic ocean, and that realization changed everything, because it meant the universe wasn't just expanding or drifting aimlessly. There was structure, there was direction, there was flow, and that raises a quiet, almost unsettling thought. If everything is moving, then we are moving too. Right now, as you sit here, listening, feeling still, your entire world is traveling through space, faster than any plane, faster than any bullet, carried along with everything else. And yet, there is no sensation of motion, no wind, no vibration, no sound, just stillness. A stillness that hides something much deeper, something vast, something that connects galaxies across unimaginable distances, something that suggests we are not just floating in space, we are being carried. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. Now that we know everything is moving, it brings up a quiet, almost surprising thought. What about our own home? Not just Earth, not just the sun, but the entire galaxy we belong to. Is it standing still? Or is it moving too? At first, it's easy to imagine the Milky Way as something stable, like a giant island in space, a place where everything inside might move, but the whole structure itself stays in one place. But that idea doesn't hold up. The Milky Way is not standing still. It is traveling, and it is moving at a speed that's hard to picture. Right now, our galaxy is drifting through space at around 600 kilometers per second. That's about 2.1 million kilometers per hour. To make that easier to imagine, if you could fly around Earth at that speed, you could circle the planet more than 50 times in just 1 hour. And yet, we feel nothing. So what does it mean for an entire galaxy to move? It helps to picture the Milky Way not as a flat picture, but as a spinning city of stars. Hundreds of billions of stars, all orbiting around a central region. If you could step outside and look at it from far away, it would look like a glowing spiral, slowly turning. But here's the important part. While it spins, it is also drifting, just like a spinning frisbee that is also flying forward. So there are two motions happening at the same time. The internal motion, stars orbiting within the galaxy, and the external motion, the entire galaxy moving through space. Now you might wonder, moving toward what? That's where things become more interesting. Scientists noticed that our galaxy is not just drifting randomly. It's moving in a specific direction, and not just our galaxy. Many nearby galaxies are moving in that same general direction too. It's like being in a crowd where everyone slowly begins walking the same way, even if they started in different places. At first you might not notice, but over time, the pattern becomes clear. So what could cause something like that? Why would entire galaxies, each containing billions of stars, move together? The answer begins with something very familiar: gravity. We usually think of gravity as something that pulls objects toward Earth or something that keeps the moon in orbit. But gravity doesn't stop there. It works on every scale, from small objects all the way up to galaxies. And when you have something massive enough, its pull can reach across enormous distances. So imagine a very large region of space, not empty, but filled with matter, stars, gas, dust, and something we'll talk more about later, something invisible. If enough mass gathers in one area, it begins to pull, slowly at first, then more strongly. And over time, it can influence the motion of entire galaxies, including ours. Now here's a question that might come to mind. If the Milky Way is moving that fast, why doesn't it look like we're rushing through space? Why don't we see stars streaming past us? The answer comes back to distance again. The stars we see are part of the same system. They're moving with us. It's like being inside a train. If you look at the passengers inside, everything feels still. But if you look out the window, you start to notice motion. Even then, if the landscape is very far away, it can still feel slow. In space, everything is so far apart that even fast motion appears gentle, calm, almost frozen. Now there's another layer to this. The Milky Way is not traveling alone. It has neighbors, nearby galaxies, including one you might have heard of, the Andromeda Galaxy. And here's something surprising. While the Milky Way is moving through space in one direction, Andromeda is actually moving toward us, slowly but steadily. So does that mean we're going to collide? Yes, but not anytime soon. The collision is expected to happen in about 4 to 5 billion years. That's such a long time that it's hard to fully grasp. If all of human history were a single day, that event would happen thousands of years into the future. And even when it does happen, it won't be like cars crashing. Space is so empty that most stars will pass by each other without ever touching. But the shapes of the galaxies will change. They will merge, slowly, over time. So even as the Milky Way travels through space, it is also part of a larger dance. A slow, graceful movement with other galaxies. Now here's something people often misunderstand. When we say the galaxy is moving, it doesn't mean it's moving through empty space, like a ship sailing across a calm ocean. Space itself is expanding, so in a way, everything is also being carried apart at the same time. This can feel confusing. How can things move towards something while space itself is stretching? The answer is that both are happening together. On very large scales, space expands, but on smaller scales, gravity pulls things together. So galaxies can still move toward massive regions, even while the universe as a whole grows larger. It's like dots on a balloon. As the balloon expands, the dots move away from each other, but if some dots are connected by rubber bands, they can still pull toward each other. Now imagine our galaxy, carried along by both of these effects, pulled in certain directions by gravity, and gently stretched away from others by the expansion of space. And all of this is happening right now, quietly, without any sign or feeling. Which leads to another simple but powerful thought. If our entire galaxy is moving, and we are inside it, then every moment of your life has been spent in motion. Every step you've taken, every breath, every quiet moment, all of it happening while traveling through space at incredible speed. And yet, it feels like stillness. That contrast between motion and calm is one of the strangest things about the universe, because it reminds us of something easy to forget. We are not observers standing outside the universe. We are part of it, carried within it, moving along with it. And as scientists kept looking deeper, mapping the motion of galaxies, a bigger pattern began to appear. Not just individual movement, not just galaxies drifting on their own, but something larger, a shared direction, a kind of hidden current. And that raises a quiet question. If our galaxy is moving, and many others are moving the same way, then where exactly are we all going? Now, let's gently zoom in a little closer. We've been talking about galaxies, vast, glowing structures made of billions of stars, and we've seen that even something as massive as the Milky Way is not still. But what about something closer to us? What about our sun and everything around it? It might feel like the sun is fixed in place, sitting at the center while the planets circle around it. That's the picture many of us grow up with, and in a way, that picture is true. The planets do orbit the sun. Earth, along with the other planets, follows a steady path around it, completing one full loop every year. But here's the part that's easy to miss. The sun itself is moving, and because we are bound to it, we are moving with it too. So even as Earth travels around the sun, the entire solar system is also traveling through the galaxy at the same time. It's like being on a merry-go-round that is itself placed on a moving train. There are layers of motion, all happening together. Let's take it one step at a time. First, Earth spins. Right now, as you sit or lie still, the planet beneath you is rotating. At the equator, this spin reaches speeds of about 1,600 kilometers per hour. That's fast enough to travel from one city to another in less than an hour. But we don't feel it. Why? Because everything around us is spinning at the same speed. The air, the ground, even our bodies, all part of the same motion, so it feels still. Now, on top of that, Earth orbits the sun. This motion is even faster. Earth moves around the sun at about 107,000 kilometers per hour. To picture that, imagine crossing an entire country in just a few minutes. And yet, again, no sensation. Just calm. Now here's where it becomes even more interesting. The sun, which seems like the center of everything, is not staying in one place either. It is orbiting the center of the Milky Way. And it does this at a speed of about 828,000 kilometers per hour. That's fast enough to circle the entire Earth more than 20 times in a single hour. But because the galaxy is so large, one full orbit takes about 225 million years. That means the last time the sun was in this exact position in the galaxy, dinosaurs hadn't even appeared yet. So when you think about your place in the universe, it's not just where you are, it's also when you are in a much larger journey. Now here's a question that often comes up. If the sun is moving that fast, are we being left behind? Why doesn't Earth drift away? The answer is simple. Gravity holds everything together. The sun's gravity keeps Earth in orbit, just like Earth's gravity keeps the moon close. So even though the sun is racing through space, it carries everything with it. Planets, asteroids, comets, all traveling together like a family moving through a vast, dark ocean. Now try to picture this. Earth is spinning. At the same time, it's orbiting the sun. At the same time, the Sun is orbiting the center of the galaxy. And at the same time, the entire galaxy is moving through space. All of these motions are layered together. So what does our actual path look like? Is it a circle? A straight line? Not quite. It's more like a spiral. As Earth orbits the Sun, and the Sun moves forward, our path through space forms a kind of swirling pattern, like a ribbon twisting as it moves, or like a corkscrew shape stretching forward. This means that every second, you are somewhere new in the universe. Not just slightly different, but completely new. If you could leave a trail behind you, marking every place you have ever been, it would stretch far beyond anything you could imagine. Now here's something that surprises many people. Even though all of this motion is happening, space doesn't feel crowded. There are no collisions, no sudden changes. Everything moves in smooth, predictable paths. Why? Because space is incredibly empty. The distances between objects are so large that even fast movement rarely leads to anything bumping into something else. To give you a sense of that emptiness, if the Sun were the size of a basketball, Earth would be a tiny bead, about 25 meters away, and the nearest star? It would be thousands of kilometers away. So even though we are moving fast, there is plenty of space to move through. Now, there's a common idea that can be a bit misleading. Some people imagine space as having a fixed background, like a stage where everything moves, but in reality, there is no fixed center, no absolute still point. Everything is moving relative to everything else. So when we say the solar system is moving, we're describing its motion compared to other stars, other parts of the galaxy. It's all relative, and that makes the universe feel a little different, less like a static place and more like a flowing system. Now, here's a quiet thought to sit with. Right now, as you listen to this, you are traveling through space at incredible speed, faster than any machine ever built, faster than anything we can fully imagine. And yet, you feel completely still, safe, calm. There's no sense of rushing, no wind, no sound, just quiet. And maybe that's what makes it so fascinating, because it shows how much of reality is hidden beneath what we feel. Motion without sensation, speed without noise, a journey without any feeling of movement. And as scientists continued to study this motion, they began to notice something even more intriguing. Our solar system wasn't just moving randomly within the galaxy, it was part of a larger pattern, a shared direction, a subtle pull, something guiding not just our Sun, but entire groups of stars and galaxies. So the question slowly begins to form again. If our solar system is moving, and our galaxy is moving, then what is guiding all of it? What is shaping this motion across such vast distances? What is quietly pulling everything along? If everything is moving, then one quiet question naturally follows. Are we just drifting aimlessly, or are we moving in a specific direction? At first, scientists weren't sure. When they began measuring how galaxies move, the results seemed messy. Some galaxies moved away, some moved slightly sideways. Others seemed to come closer. It felt random, like watching leaves scattered across a wide field, each one pushed by its own small gust of wind. But as time passed, and measurements became more accurate, something subtle began to appear. A pattern, not obvious at first, but steady, consistent, and once it was noticed, it couldn't be unseen. Many galaxies, including our own, were moving in a similar direction, not exactly the same path, but clearly influenced by something larger. It was like looking at a crowd from far above, up close. Each person walks slightly differently. Some turn, some slow down, some change direction, But from a distance, you start to see the flow of the crowd. Everyone is moving, generally, the same way. So what does that mean for us? It means that our galaxy is not just wandering through space. It is part of a larger movement, a shared journey. Now here's something important to understand. This direction isn't something you can point to in the sky easily. There's no bright sign or glowing marker showing where we were headed. Instead, scientists had to figure it out by studying the light from distant galaxies. And this is where things get really interesting. When an object moves, the light it gives off changes slightly. If it moves away from us, its light shifts toward red. If it moves toward us, it shifts toward blue. This is called the Doppler effect. You've probably experienced something similar with sound. When an ambulance passes by, the pitch of its siren changes. As it comes closer, the sound feels higher. As it moves away, it feels lower. Light behaves in a similar way. So by studying these tiny shifts in light, scientists could tell how galaxies were moving. Not just how fast, but also in which direction. And when they mapped all of this out, a pattern appeared. Galaxies across vast regions of space were not just moving randomly. They were drifting toward a certain part of the universe, including us. Now, let's pause for a moment. If many galaxies are moving toward the same region, what could be causing that? The simplest answer is gravity. Something in that direction must be pulling them. But here's where it becomes a little mysterious. When scientists looked in that direction, they couldn't see anything obvious that was large enough to explain it. No single bright object, no clear structure, nothing that matched the strength of the pull they were measuring. So what does that mean? It suggests that whatever is influencing this motion is either very far away, or hidden, or both. Now imagine standing in a dark room. You feel a gentle pull, like something is drawing you forward. But you can't see what it is. You only know it's there because of the effect it has on you. That's a bit like what scientists were experiencing. They could see the motion, they could measure the direction, but the source of that motion remained unclear, and that made things even more interesting, because it hinted that the universe might be structured in ways we don't fully understand yet. Now here's a question that might come to mind. If everything is moving in a direction, are we heading somewhere specific, like a destination? Not exactly. It's not like a road with a clear endpoint. Instead, it's more like being caught in a current. Imagine floating in a wide river. You're not steering. You're not choosing a destination, but the water carries you steadily in a certain direction. That's what this motion feels like on a cosmic scale. Galaxies, including ours, are being carried along by gravitational currents, and these currents are shaped by massive structures spread across space. Now, there's another detail that makes this even more fascinating. The direction we're moving toward lies behind a dense region of our own galaxy, a part of the sky filled with thick clouds of gas, dust, and stars. So even if there is something there, something massive, our view is blocked. It's like trying to see what's on the other side of a mountain while standing in a deep fog. You know something is there, but you can't see it clearly, and that adds a quiet sense of mystery, because it means that even with all our technology, there are still parts of the universe hidden from us, not because they're too far, but because something is in the way. Now let's return to that idea of direction. If you could somehow step outside the Milky Way and look at it from far away, you would see it moving, not just spinning, but drifting, and nearby galaxies drifting too, all gently pulled in a similar direction, like a slow, silent migration. And it's happening over enormous distances so large that even light, traveling at its incredible speed, takes millions of years to cross them. To give you a sense of that, Light can travel around Earth more than 7 times in just 1 second. And yet, to cross the distance between some galaxies, it takes millions of years. So when we talk about galaxies moving together, we're talking about motion across spaces so vast, they almost feel unreal. And yet, it's happening right now, quietly, slowly, steadily. Now here's something worth reflecting on. Even though we are part of this movement, we have no direct control over it. We can't stop it. We can't change its direction. We are passengers, carried along by forces far beyond our scale. And yet, at the same time, we can understand it. We can observe it. We can trace the patterns and begin to see the bigger picture. And as that picture becomes clearer, it leads to an even deeper idea. This shared direction, this quiet drift of galaxies, is not random. It is part of something larger, a structure, a flow, a kind of invisible map, guiding motion across the universe. And once you begin to see that, a new question begins to form. If galaxies are moving together, then what is this larger flow they are part of? What does it look like on the biggest scale, and how far does it reach? When scientists began to notice that galaxies were moving in similar directions, they needed a way to describe this quiet, shared motion, so they gave it a simple name: cosmic flow. At first, the name might sound a little abstract, but the idea behind it is surprisingly easy to picture. Imagine standing beside a wide river. On the surface, you see small ripples, little swirls, tiny waves moving in different directions. If you focus only on those details, everything looks chaotic. But if you step back and watch the river as a whole, you begin to see something else. A steady movement, a clear direction. The water is flowing. Now take that image and stretch it across the entire universe. Galaxies are like those ripples on the surface. Up close, their motion can seem random, but on a larger scale, they are part of a flow, a slow, steady movement shaped by gravity. That is what cosmic flow means. It's not a single object pulling everything. It's not a straight path, like a road. It's a pattern of motion, spread across vast regions of space. Now here's a question that often comes up. If space is mostly empty, how can there be a flow? What exactly is flowing? The answer is matter, galaxies, gas and unseen mass, all moving under the influence of gravity. Even though space feels empty, it's filled with structure, and that structure creates gentle currents, not like wind you can feel, but more like invisible pulls that guide motion over long periods of time. Think of it like this: if you drop a leaf into still water, it barely moves. But if there's even a slight current, the leaf begins to drift, slowly at first, then steadily. Now imagine that current stretching across millions of light years. That's what galaxies are experiencing. They are not just sitting in space, they are being carried. Now, it's important to clear up a small misunderstanding here. Some people think that cosmic flow means everything is being pulled into one single point, like water going down a drain. But that's not quite right. The universe is far more complex. There are many regions of mass, many areas with stronger gravitational pull. So instead of one simple flow, there are overlapping flows, like rivers that branch, merge, and curve around each other. In some areas, galaxies move toward large clusters. In others, they drift away from less dense regions, and all of these motions combine, creating a kind of cosmic map of movement. Now you might wonder, how do scientists even detect something like this? After all, we can't step outside the universe and watch it from above. So how do we see the flow? The answer comes from careful observation. By measuring the speed and direction of thousands of galaxies, scientists can map how they move relative to each other. It's like tracking thousands of boats in a vast ocean. At first, each boat seems to move on its own. But when you map all their paths together, patterns begin to appear. You start to see currents, you start to see flow, and that's exactly what happened with galaxies. As more data came in, the picture became clearer. Galaxies were not moving randomly. They were following large-scale patterns, and those patterns pointed towards something bigger. Now, here's something fascinating. These flows happen over incredibly long timescales. Nothing changes quickly. There are no sudden shifts or sharp turns. Everything moves slowly, gently, over millions and billions of years. To give you a sense of that, if a galaxy changes its direction, even slightly, it can take millions of years for that change to become noticeable. So from our point of view, everything feels almost frozen. But over time, the motion becomes clear. Now let's pause and ask something simple. If cosmic flow is real, and we are part of it, then where are we in this flow? Are we near the center, on the edge, or somewhere in between? The answer is, we are part of a larger region moving together. A kind of neighborhood of galaxies, all sharing a similar motion. We'll explore that more later, but for now it's enough to understand this. We are not moving alone. Our galaxy is part of a group, and that group is part of an even larger flow. Now here's another thought that might come to mind. If everything is flowing, does that mean the universe is like a giant river? In a way, yes, but it's more complex than that, because the river itself is shaped by gravity, and gravity depends on where matter is located. So the flow changes depending on the structure of the universe. Dense regions pull more strongly, empty regions have less influence, and this creates a kind of invisible landscape, a landscape made not of solid ground, but of gravitational forces, and galaxies move across this landscape, following its shape. Now imagine walking across a valley. You don't need to see the slope to feel it. Your path naturally follows the shape of the land. In the same way, galaxies follow the shape of gravity. They move along paths shaped by mass, even if that mass is invisible. And that leads to something very important. Much of what shapes cosmic flow cannot be seen. There are forces at work that don't show up as light. We can't point to them directly, but we can see their effects. We can see how galaxies move, and from that motion, we can begin to understand the unseen. Now here's a quiet realization. The universe is not just expanding or drifting. It has structure, it has direction, it has flow, and we are inside it, carried along without feeling it, moving through space without noticing. And as scientists continued to map this flow, they began to notice something even more surprising. At smaller scales, everything still looked messy, chaotic, unpredictable. But at larger scales, order began to appear, patterns became clearer. And that raised a new question. Why does motion look random up close, but organized from far away? What changes when we step back and see the bigger picture? When we look up at the sky, or even when scientists first began studying galaxies, everything seemed a bit messy. Some galaxies moved one way, others moved in a different direction. Some sped up, others slowed down. It didn't feel organized. It felt random, and that made sense at the time. After all, if you throw a handful of leaves into the air, they scatter in all directions. There's no clear pattern, just motion. So for a while, people believed the same thing about the universe, that galaxies were simply drifting, each one following its own path, without any larger order. But that idea didn't last, because as more observations came in, something started to change. The randomness wasn't quite as random as it seemed. Let's slow down and picture something simple. Imagine standing on a busy street. Cars are passing by. Some turn left, some turn right, some stop, some speed up. If you focus on just one car, its movement might feel unpredictable. But if you climb up to the top of a tall building and look down, you begin to see patterns. You notice lanes. You see traffic flowing in certain directions. You start to understand that what looked random is actually organized. The same thing happens in the universe. When we focus on small regions, just a few galaxies at a time, their motion can feel chaotic. Each galaxy has its own local influences. Nearby gravity pulls it slightly this way or that way. Small interactions create little changes in direction, so up close, it looks messy. But when we step back, when we look at thousands or even millions of galaxies together, a different picture appears. Patterns, large-scale patterns. Galaxies moving together, groups drifting in similar directions, flows forming across vast distances. So the randomness was never truly random. It was just hard to see the bigger structure from a close view. Now here's a question that naturally comes up. Why does this happen? Why does motion look chaotic up close, but organized from far away? The answer lies in scale. At small scales, local forces dominate. Think of it like a small pond. If you drop a stone into it, ripples spread out in all directions. Wind can push the water. Tiny currents form. The surface becomes unpredictable. But if you step back and look at the entire pond over time, you might notice a general flow. Water slowly moving toward one side. Evaporation changing the level. Larger patterns shaping the system. Now imagine something much bigger. Not a pond, but an ocean. On the surface, waves crash in every direction. But beneath that surface, there are massive currents. Slow, steady, powerful. Currents that move entire bodies of water across the planet. The universe works in a similar way. At small scales, galaxies interact with nearby neighbors. These interactions create small, complex motions. But at larger scales, gravity from massive regions begins to dominate, and that creates flow. Now here's something interesting. Even though galaxies are incredibly far apart, they still influence each other. Gravity doesn't need contact. It reaches across space, so even distant structures can shape motion. And over time, those influences add up. Now let's pause for a moment. If the universe has these large-scale patterns, why didn't we notice them right away? Why did it take so long to see the flow? The answer is simple. We needed more data. In the past, scientists could only observe a limited number of galaxies. It was like trying to understand a forest by looking at just a few trees. You might notice details, but you missed the overall shape. As technology improved, we began to see more. Hundreds of galaxies, then thousands, then millions. And with that larger view, the hidden patterns began to reveal themselves. Now here's another thought that can feel a bit surprising. The universe is not perfectly uniform. It's not the same everywhere. Some regions are dense, filled with galaxies. Others are more empty, with very little matter. This uneven distribution creates differences in gravity. And those differences shape motion. Galaxies near dense regions feel a stronger pull. Galaxies near emptier regions drift differently, so the flow of the universe is shaped by its structure. Now imagine walking through a landscape. If the ground is flat, you can move in any direction easily. But if there are hills and valleys, your path naturally changes. You might walk downhill without even thinking about it. You might avoid steep climbs. In the same way, galaxies follow the shape of gravity. They move along paths created by the distribution of mass, and that's why motion looks organized at large scales, because it follows a kind of invisible terrain. Now here's a question you might be thinking. If everything follows these patterns, does that mean the universe is predictable? In some ways, yes. We can model large-scale motion. We can predict general flows, but at smaller scales, things remain complex. Local interactions, small variations, can still create differences. So the universe is both predictable and unpredictable at the same time, ordered, yet detailed. Simple in its large structure, but complex in its smaller parts. And that balance is part of what makes it so fascinating. Now, let's return to that idea of illusion, the illusion of randomness. It's not that the universe is chaotic. It's that our perspective can be limited. When we look at small pieces, we see noise. When we look at the whole, we see pattern. And that idea applies to many things, not just space. But here, it reveals something important. The universe has structure. It has direction. It has flow, and those flows are not obvious at first glance. They reveal themselves slowly, as we step back and see more. Now here's a quiet realization to sit with, right now, as everything around you feels still. You are part of a system that is deeply organized, moving along paths shaped by forces you can't see, following patterns that stretch across unimaginable distances. And yet, it all feels calm, still, almost motionless. But beneath that stillness, there is order, there is movement, there is a hidden structure guiding everything. And as scientists looked deeper into this structure, they began to discover something even more remarkable. The universe is not just filled with galaxies scattered randomly, it is arranged in a vast, interconnected network. A kind of cosmic web stretching across space. And that raises a new question. What does this web look like? And how does it shape the motion of everything within it? When we hear the word gravity, we usually think of something simple. An apple falling from a tree, a ball dropping to the ground, or the feeling of weight that keeps our feet firmly planted on Earth. It feels familiar, small, local. But gravity is not just a force that works here on Earth. It reaches far beyond, stretching across space, shaping the motion of entire galaxies. And once we begin to see gravity at that scale, everything starts to feel different. Let's start with something simple. If you drop a pen, it falls. Why? Because Earth pulls it downward. Now imagine something much larger, like the moon, doesn't fall to Earth in a straight line. Instead, it moves sideways at the same time, creating an orbit. It's constantly falling, but also constantly missing. Now take that same idea and expand it. Planets orbit stars. Stars orbit the center of galaxies. And galaxies themselves are influenced by even larger gravitational forces. So gravity isn't just pulling things down. It's guiding motion, shaping paths, creating structure. Now here's a question that often comes up. If gravity is pulling everything together, why doesn't the universe just collapse into one giant clump? Why isn't everything crashing into everything else? The answer lies in balance. Objects in space are not just sitting still, they are already moving. So instead of falling straight inward, they move along curved paths, like a ball tied to a string, spinning in a circle. If you let go, it flies off. But as long as the string holds, it follows a path. In space, gravity is like that string. It keeps things connected, but motion keeps them from collapsing. Now, let's take a step back. What happens when you bring together something incredibly massive, something much larger than a planet or even a star? Its gravity becomes stronger. Not just a little stronger, but vastly stronger. strong enough to influence objects across enormous distances. To give you a sense of scale, if Earth's gravity can pull an apple from a few meters away, a massive galaxy cluster can influence other galaxies from millions of light years away. That's like feeling the pull of something across a distance so large, light itself takes millions of years to travel it. Now imagine many of these massive regions spread across space, each one pulling, each one shaping motion. Their effects overlap, combine, and create the flows we talked about earlier. This is gravity at a cosmic scale, not a single pull, but a network of influences. Now here's something important to understand. Gravity doesn't need contact. It doesn't need a medium. It works through space itself. Even in complete emptiness, gravity reaches out. So even if galaxies are separated by vast distances, they are still connected, still influencing each other. Now, let's pause for a moment. If gravity shapes motion at such large scales, can we see it directly? Not exactly. We can't see gravity itself, but we can see its effects. We can see how objects move. We can see how light bends around massive regions. We can see patterns, and from those patterns, we understand the force behind them. It's a bit like wind. You can't see the wind directly, but you can see leaves moving. You can feel it on your skin. You can watch waves forming on water. And from that, you know the wind is there. Gravity works in a similar way. Now here's a common misunderstanding. Some people think gravity is only strong when objects are close together. And it's true that gravity becomes stronger with distance. But even weak gravity, acting over long periods of time, can have a huge effect. Think of it like a gentle push. If you push something lightly for just 1 second, it barely moves, but if you keep pushing steadily for hours, it will travel far. In the universe, gravity has billions of years to work, so even small pulls can shape motion across vast distances. Now imagine galaxies slowly drifting under these influences, not rushing, not colliding suddenly, but gradually, following the paths shaped by gravity. This is what creates the cosmic flow. This is what gives direction to motion. Now here's something even more fascinating. Gravity doesn't just act between visible objects. It also acts on things we can't see. There is mass in the universe that doesn't give off light. We can't observe it directly, but we know it's there because of the way it affects motion. We'll explore that more later, but for now, it's enough to understand this is only part of the story. There is more mass, more influence than meets the eye, and that hidden mass plays a huge role in shaping the universe. Now let's return to a simple image. Imagine placing a heavy ball on a stretched fabric. The fabric bends under its weight. If you roll a smaller ball nearby, it curves toward the heavier one. That's a simple way to picture gravity. Now imagine not just one ball, but many, different sizes, different positions, each one bending the fabric. The result is a complex landscape of curves and slopes. And anything moving across that surface follows those curves. That's what space is like, a landscape shaped by mass, and galaxies move across it, guided by those shapes. Now here's a quiet thought. Right now, as you sit in stillness, you are part of this system. You are inside a structure shaped by gravity, moving along paths created by forces far beyond anything we can see directly. And yet, it feels calm, stable, almost unmoving. But beneath that calm, gravity is always at work, gently pulling, guiding motion, shaping the universe on the largest scale. And as scientists continued to study this, they began to notice something even more intricate. Gravity wasn't just creating simple flows. It was organizing matter into a vast network, a structure that connects galaxies across space, a structure often described as a web. And that leads to the next question. What does this cosmic web look like? And how does it hold everything together? If you could somehow step far outside the universe and look back at it from a distance, you might expect to see something simple. Maybe galaxies scattered evenly, like dots on a smooth surface, or perhaps a random spread, like grains of sand thrown across a table. But that's not what we see. The universe is not arranged randomly. It has structure, and not just any structure, but one that stretches across unimaginable distances. Scientists often describe it as a web, a cosmic web. Now, what does that mean? Let's picture something familiar. Imagine a spider web in the early morning. Thin strands, almost invisible, stretching outward. Some parts are thicker, where strands meet. Other areas are more open, almost empty. If light hits it just right, you can see the pattern, a network, connections everywhere. Now take that idea and expand it beyond anything you've ever seen. Instead of silk threads, imagine streams of galaxies. Instead of tiny intersections, imagine massive clusters containing thousands of galaxies. And instead of small empty gaps, imagine vast regions of space with almost nothing in them. That's the large-scale structure of the universe. Galaxies are not evenly spread. They gather along long, thin regions called filaments. These filaments stretch across space like strands in a web. And where these strands meet, matter collects, forming dense clusters, bright, crowded regions filled with galaxies. Between these filaments, there are enormous empty spaces. These are called void, regions so empty that if you were there, the nearest galaxy might be incredibly far away. To give you a sense of that emptiness, if you were in one of these voids, it would be like standing alone in a desert, so vast that even the nearest mountain is beyond the horizon, in every direction. Now here's a question that naturally comes up. Why does the universe form a web? Why not just spread everything evenly? The answer goes back to gravity. In the early universe, matter was not perfectly smooth. There were tiny differences. Some areas had slightly more mass, others had slightly less. At first, these differences were very small, almost unnoticeable, but gravity amplified them. Regions with more mass pulled in more matter, slowly growing denser, becoming emptier. Over billions of years, these small differences grew, stretching into long filaments, gathering into clusters, leaving behind vast empty spaces. And that's how the cosmic web formed. Now here's something interesting. This structure is incredibly large. Filaments can stretch across hundreds of millions of light years. That's like a thread so long that light, traveling at its fastest possible speed, would take hundreds of millions of years just to cross it, and clusters at the intersections. They can contain thousands of galaxies, each galaxy holding billions of stars. So when we talk about this web, we're talking about something almost impossible to fully imagine. Now let's pause for a moment. If galaxies are arranged along these filaments, what does that mean for their motion? It means they don't move randomly through empty space. They move along these structures, like cars following roads, or water flowing through channels. The filaments guide their paths. Gravity along these dense regions pulls galaxies inward, toward clusters. So the cosmic flow we talked about earlier is shaped by this web. Galaxies drift along filaments, moving toward denser regions. Now imagine standing on a hill, looking down at a valley. You see paths where water has carved its way through the land. Those paths guide the flow of rain. In the same way, the cosmic web guides the motion of galaxies. Now here's something that might surprise you. Most of the universe is actually empty. These voids between filaments make up a huge portion of space. So while galaxies feel numerous when we look at the night sky, they are actually concentrated in specific regions, and vast areas in between are almost completely empty. Now you might wonder, if the universe is mostly empty, why does it look so full when we look up? The answer is perspective. From Earth we see stars within our own galaxy. They fill the sky. But beyond that, the distances are so great that other galaxies appear as faint points. If you could travel far outside our galaxy and look back, you would see large empty spaces with galaxies gathered along thin strands. Now, here's a common misunderstanding. Some people imagine the universe as a flat, two-dimensional map, like a sheet with points on it. But the cosmic web exists in 3 dimensions. It stretches in all directions, up, down, across, forming a vast interconnected network. So it's more like a giant sponge or a foam with filaments and gaps extending everywhere. Now let's return to a simple thought. If galaxies are part of this web, then our galaxy is part of it too. The Milky Way is not isolated. It sits along one of these filaments, connected to other galaxies, part of a larger structure, and that means our motion is influenced by this web. We are not drifting freely. We are moving along paths shaped by this structure. The universe is not just a collection of objects. It's a connected system. Everything linked through gravity, through structure, galaxies, clusters, filaments, all part of one vast network, and we are inside it, moving along with it, without seeing the full picture, without feeling the motion, just quietly carried along. And as scientists studied this web more closely, they discovered something even more surprising. The visible matter, the stars and galaxies we can see, are only a small part of what makes up this structure. There is something else, something invisible, forming the backbone of this entire web. And that raises a deeper question. If most of the structure is unseen, then what is really holding this cosmic web together? If we continue gently exploring this idea of the cosmic web, 2 features begin to stand out more clearly: the filaments and the clusters. These are the main shapes that give the universe its structure. And once you understand them, the motion of galaxies starts to make more sense. Let's begin with filaments. Imagine long, thin strands stretching across space, not solid like a rope, but more like streams of matter. These filaments are where galaxies gather in lines, not perfectly straight, but gently curved, sometimes branching, sometimes merging. If you could see one from far away, it might look like a glowing thread dotted with tiny lights. Each light, a galaxy. Now here's something important. These filaments are enormous. Some stretch across hundreds of millions of light years. To picture that, imagine turning on a flashlight. The light travels around Earth more than 7 times in just 1 second. Now imagine that same light traveling, not for seconds, not for hours, but for hundreds of millions of years, just to cross one filament. That's the scale we're dealing with. Now, why do galaxies gather along these filaments? The answer goes back to gravity again. Matter pulls matter. Even small differences in density over long periods of time create structure. Regions with slightly more mass attract more material. Over billions of years, this creates long, connected strands, like water slowly carving channels into soft ground. Now, let's move to clusters. Where filaments meet, matter gathers. These intersections become dense regions, filled with galaxies. These are galaxy clusters. If filaments are like roads, clusters are like busy cities, places where many paths come together, places where matter collects. A single cluster can contain hundreds, sometimes thousands of galaxies, each galaxy holding billions of stars. So a cluster is not just large, it's incredibly massive. To give you a sense of that mass, if our galaxy were like a single grain of sand, a cluster would be like a whole beach, filled with countless grains. Now here's something interesting. Clusters are not quiet places. With so many galaxies close together, gravity creates interactions. Galaxies can pass near each other. They can distort, stretch, even merge over time. But remember, space is still very empty. So even in clusters, direct collisions between stars are extremely rare. It's more like two clouds passing through each other, slowly blending. Now, let's pause and ask something simple. If galaxies are found along filaments and gather in clusters, what happens in between? The answer is very little. These regions are called voids. We mentioned them earlier. They are vast, empty spaces. So the universe has a kind of pattern. Dense clusters, connected by filaments, surrounded by emptiness. Now imagine looking at a sponge. Solid parts and empty holes. Or imagine bubbles in foam, thin walls and large gaps. That's what the large-scale universe resembles. Now here's a question that might come to mind. If galaxies are arranged this way, how do they move? Do they stay fixed in these filaments and clusters, or do they travel through them? The answer is, they move along them. Galaxies drift along filaments, slowly pulled toward clusters. It's like water flowing through a network of rivers, eventually reaching larger bodies. So the motion we talked about earlier, the cosmic flow, is guided by these structures. Filaments act like pathways, clusters act like destinations. Now, this movement is not fast in human terms. It happens over millions and billions of years. But it is steady, continuous. Now imagine placing a small ball on a slightly tilted surface. It doesn't roll quickly, but it moves slowly toward the lowest point. In the same way, galaxies follow the gentle slopes created by gravity. Now here's something subtle but important. These filaments are not rigid. They are not fixed like solid beams. They evolve over time. As matter flows, filaments can grow, stretch, even change shape. Clusters can become more massive, pulling in more galaxies, so the cosmic web is not static. It's dynamic, always changing, but very slowly. Now here's a common misunderstanding. Some people imagine that clusters are the final destination, that everything eventually falls into them. But the universe is more complex than that. There are many clusters, many filaments, many flows, so motion doesn't lead to one single point. Instead, it forms a network of movements, different regions, with different paths. Now let's bring this back to something personal. Our galaxy, the Milky Way, is part of this structure. It sits along a filament, connected to other galaxies, part of a larger system. And that means our motion is shaped by these filaments and clusters. We are not drifting freely through empty space. We are following paths created by the structure of the universe. Now here's a quiet thought to reflect on. If you could zoom out far enough, you would see galaxies flowing along these strands, gathering into clusters, leaving behind vast empty spaces, a slow, silent movement across an immense network. And we are inside that network, moving with it, without seeing it directly, without feeling its pull, just quietly carried along. And as scientists studied these filaments and clusters more closely, they noticed something even more puzzling. The visible matter, the galaxies and stars, did not seem to have enough mass to create and hold this structure on their own. Something was missing, something unseen, but incredibly important. And that leads to the next question. If what we can see is not enough, then what is really forming the backbone of this cosmic web? As scientists mapped the filaments and clusters of the universe, something didn't quite add up. The structure was there, the motion was there. Galaxies were clearly being guided, pulled, organized into this vast web, but when they tried to explain it using only what they could see, it didn't work. There wasn't enough visible matter, not enough stars, not enough gas, not enough galaxies. It was like trying to build a massive bridge using only a few thin wires. It shouldn't hold, and yet the universe does. So naturally, a question began to form. What are we missing? What is providing the extra pull, the extra structure, the hidden strength behind all of this? The answer, as strange as it sounds, is something we cannot see. It's called dark matter. Now, that name might sound mysterious, even a little intimidating, but the idea itself can be understood in a simple way. Dark matter is matter that does not give off light. It doesn't shine, it doesn't glow, it doesn't reflect, so we can't see it with our eyes or even with our most powerful telescopes. But even though it's there, because of what it does, let's take a simple example. Imagine watching leaves move across the ground. You don't see the wind directly, but you know it's there because the leaves are moving. In the same way, we don't see dark matter, but we see how galaxies move, and that motion tells us something unseen is influencing them. Now here's something that surprised scientists. There appears to be far more dark matter in the universe than visible matter. In fact, most of the mass in the universe is dark. To picture that, imagine a city at night. You see the lights from buildings, cars, and streets. But now imagine that everything you can see is only a small part of what's actually there. The rest of the city, the roads, the structures, the foundations, are hidden in darkness. That's what the universe is like. The stars and galaxies we see are just the glowing parts. The underlying structure is mostly invisible. Now let's return to the cosmic web. If we could somehow see dark matter, the web would look much more complete. The filaments would appear thicker, more defined. The clusters would look heavier, more connected, because dark matter forms the backbone of this structure. It's what gives the web its shape. Now here's a question that might come to mind. How does dark matter affect galaxies? The answer is through gravity. Even though dark matter doesn't interact with light, it still has mass. And mass creates gravity. So dark matter pulls on galaxies, just like visible matter does. In fact, it pulls even more, because there's so much of it. Now imagine a galaxy like the Milky Way. You might think that the stars we see make up most of its mass, but they don't. The galaxy is surrounded by a large halo of dark matter, an invisible cloud extending far beyond the visible stars. This halo acts like a kind of gravitational anchor, holding the galaxy together. The outer stars would move too fast and drift away, but they don't, because something unseen is keeping them in place. Now let's pause and ask something simple. If dark matter is everywhere, why haven't we detected it directly? Why can't we just measure it? The answer is, it doesn't interact in the ways we're used to. It doesn't collide with light. It doesn't emit signals we can easily detect. It passes through normal matter, almost as if it's not there. So we can't see it, touch it, or capture it directly. But we can measure its effects. We can see how galaxies rotate. We can observe how light bends around massive regions. We can map the motion of clusters, and all of these observations point to the same conclusion. There is more mass than we can see. Now here's a common misunderstanding. Some people think dark matter is just regular matter hiding in darkness, like black dust or invisible gas, but that's not quite right. Dark matter behaves differently. It doesn't clump together in the same way. It doesn't form stars. It doesn't create light. It exists in a different form, one we are still trying to understand. Now let's return to the idea of cosmic flow. If dark matter forms the backbone of the universe, then it also shapes the flow. Galaxies don't just follow visible structures, they follow the gravitational pull of dark matter. So the paths they take, the directions they move, are guided by something we cannot see. Now imagine walking through a landscape at night. You can't see the hills and valleys clearly, but you can feel them. You can sense when you're going uphill or downhill. In the same way, galaxies move through a landscape shaped by dark matter. They follow its invisible contours. Now here's a quiet realization. Most of what is shaping the universe is hidden. The stars we see are only a small part of the story. The real structure, the deeper framework, is invisible, and yet it's what guides everything. Now think about that for a moment. Right now, as you sit in stillness, you are inside a galaxy, held together by something you cannot see, moving through a web shaped by forces you cannot directly observe, carried along by the pull of invisible matter. And yet, it all feels calm, stable, unchanging. But beneath that calm, there is a hidden structure, a silent framework, holding everything together, guiding motion across the universe. And as scientists continued to study this invisible influence, they began to realize something even more profound. If most of the universe is made of dark matter, then what we see is only a small fraction of reality. And that raises a deeper question. If so much of the universe is invisible, then how much of it are we truly able to understand? When we look up at the night sky, it feels full, stars scattered everywhere, a soft band of light from the Milky Way stretching across the darkness. On a clear night, it can feel like the universe is overflowing with light. But here's something quietly surprising. What we see is only a tiny part of what's actually there. Most of the universe is invisible, not hidden behind distance alone, but hidden by its very nature. And that raises a simple question. Why can't we see it? Let's begin with something familiar. Our eyes can only detect a small range of light. We call it visible light. It includes the colors we know: red, orange, yellow, green, blue, and violet. But beyond that range, there are other kinds of light. Radio waves, infrared, ultraviolet, X-rays, gamma rays. All of these exist, but we can't see them with our eyes. It's like listening to a conversation, but only hearing a few words. The rest is there, but outside your range. Now, telescopes help us extend that range. They allow us to detect different kinds of light, to see things that would otherwise remain hidden. But even with all our technology, there are still parts of the universe that don't emit any light at all. And that brings us back to dark matter. Dark matter doesn't glow. It doesn't reflect light. It doesn't interact with light in a way we can detect. So no matter how powerful our telescopes become, it remains invisible. Now here's a question that might come to mind. If something doesn't give off light, how do we even know it exists? The answer is through its effects. We see how galaxies rotate. We observe how clusters hold together. We measure how light bends as it passes through space. And all of these observations tell us there is more mass than we can see. It's like noticing footprints in the sand. You don't see the person, but you know they were there. Now, dark matter is only part of the story. There is another reason why much of the universe remains unseen: distance. The universe is incredibly large, so large that light takes time to travel. When you look at a distant galaxy, You are seeing it as it was in the past, sometimes millions or even billions of years ago. But there are regions so far away that their light hasn't had enough time to reach us yet. It's still traveling, still on its way. So those parts of the universe remain invisible to us for now. To picture this, imagine turning on a flashlight in a dark room. The light spreads outward, but it takes time to reach the far walls. If you look into the distance before the light arrives, that area remains dark. The same thing happens in the universe. Light is always traveling, but it hasn't reached everywhere. Now here's something else to consider. Even when light does reach us, it can be blocked. Our own galaxy is filled with dust and gas. Certain regions of the sky are harder to see through. It's like trying to look through thick fog. You know something is beyond it, but your view is limited. So even nearby structures can be hidden simply because something is in the way. Now let's pause for a moment. If most of the universe is invisible, what does that mean for our understanding? It means we are only seeing a fraction of reality, like looking at an iceberg where most of it lies beneath the surface, or like hearing a song but only catching a few notes. There is much more beyond what we can directly observe. Now here's a common misunderstanding. Some people think that invisible means unimportant. But in the universe, the opposite is true. What we can't see often plays the biggest role. Dark matter shapes the structure. Hidden regions influence motion. Unseen forces guide the flow. So the visible universe is just the surface. The deeper structure lies beyond our sight. Now imagine walking through a forest at night. You can only see what your flashlight reveals. A few trees, a small path. But beyond that light, the forest continues. Wide, dense, full of things you can't see, but know are there. That's what exploring the universe is like. We are shining a light into a much larger reality. Now here's a question that often comes up. Will we ever be able to see everything? The honest answer is, probably not. There are limits to what we can observe. Limits set by distance. Limits set by the nature of light. Limits set by the universe itself. But even with those limits, we can still learn. We can still understand patterns. We can still uncover the structure through careful observation. Now let's return to something simple. Right now, as you look around, everything you see feels complete, solid, visible. But the universe reminds us that what we see is only a part of the whole. There is always more, beyond our perception, more structure, more motion, more hidden layers. And yet, even without seeing everything, we are part of it, moving within it, carried along by forces we cannot directly observe. Now here's a quiet thought to sit with. If most of the universe is invisible, then our sense of stillness, our sense of understanding, is only based on a small piece of the picture. Beneath that, there is a deeper reality, a hidden framework shaping everything. And as scientists continue to explore this hidden universe, they began to map something even larger. A vast region where galaxies share the same motion, kind of cosmic neighborhood, defined not by boundaries we can see, but by the way everything flows together. And that leads to the next question. What is this region? And how does it connect to the motion we are part of? As scientists continued mapping the motion of galaxies, something remarkable began to take shape. It wasn't just small groups moving together. It wasn't just clusters connected by filaments. There was something larger, much larger, a vast region where galaxies shared a common motion, a region so large it stretched across hundreds of millions of light years. This region was eventually given a name, Laniakea, a word that means immense heaven. And when you begin to understand what it represents, that name starts to feel fitting. Now, what exactly is Laniakea? At first, you might think it's just another structure, like a cluster or a group of galaxies. But it's different. It's not defined by what we see. It's defined by how things move. That's what makes it special. Scientists didn't just look at where galaxies are located. They looked at how they travel, the direction they drift, the way their motion connects to others. And when they mapped those movements, they noticed something surprising. A huge number of galaxies, including our own, were all flowing toward the same general region, not randomly, not loosely, but as part of a connected system. It was like watching streams of water, all feeding into the same basin. Now here's a question that might come to mind. How big is this region? The answer is almost impossible to imagine. Laniakea spans about 500 million light-years across. To picture that, light, traveling at its fastest speed, would take 500 million years just to cross it. If you started that journey when the first complex life began on Earth, you still wouldn't have reached the other side today. That's the scale we're talking about. Now imagine everything inside that region. Hundreds of thousands of galaxies, each containing billions of stars, all part of the same system, all connected, not by physical boundaries, but by motion. Now, let's pause and think about something simple. If Laniakea is defined by motion, what does that mean? It means that galaxies inside this region are not just near each other, they are moving together. Their paths are linked. Their motion flows toward a shared direction. It's like being part of a large river system. Different streams, different paths, but all leading toward the same place. Now here's something interesting. Before this discovery, scientists grouped galaxies based mostly on their positions. Clusters, superclusters, structures based on where things are located. But Laniakea introduced a new way of thinking. Instead of asking, where are these galaxies? The question became, how are they moving? And that change revealed something deeper. Because motion tells us about influence. It tells us about gravity. It shows us how structures are connected beyond what we can see. Now here's a question you might be wondering. Where are we in all of this? The Milky Way, our home galaxy, is part of Laniakea. We are inside this vast region, moving along with it, carried by the same flow. Now imagine standing inside a massive, slow-moving current. You don't feel the motion. You don't see the full extent, but you are part of it. That's our situation. Now, let's go a little deeper. If Laniakea is so large, is it the entire universe? No, it's just one region among many. The universe contains other superclusters, other flows, other massive structures, but Laniakea is our local neighborhood, the region we belong to. Now here's something that often surprises people. Even though Laniakea is incredibly large, it's not tightly bound. It's not like a solid object, it's more like a region of influence, a zone where gravity shapes motion in a certain way. So its boundaries are not sharp, they are defined by how galaxies move, where the flow changes direction, where one region's influence ends and another begins. Now, imagine standing on a hillside. Rainwater flows down in different directions. Some drops go one way, others go another. The point where that change happens marks a boundary. Not something you can see directly, but something defined by motion. That's how Laniakea is defined. Now here's a quiet realization. Our place in the universe is not just about location. It's about motion. We are part of a flow, part of a system that extends far beyond what we can see. And that system is guiding our movement, even now. Now you might wonder, if everything in Laniakea is moving together, what is it moving toward? That question leads to something even more mysterious, because at the center of this flow, there appears to be a region of strong gravitational pull, a place drawing galaxies inward. But when scientists looked in that direction, they couldn't see it clearly. Something was there, but hidden, obscured by the dense regions of our own galaxy, and that made things even more intriguing, because it meant that this vast flow, this entire region of galaxies moving together, was being guided by something we couldn't fully observe. Now imagine being part of a massive crowd, all walking in the same direction. You don't know exactly what's ahead. You can't see the destination clearly, but you can feel the movement. You can sense the direction. That's what being inside Laniakea is like. Now here's something to sit with. Right now, as you feel still, you are part of this immense structure, a region so vast. It stretches across hundreds of millions of light years, a system defined not by what we see, but by how everything moves together. And yet, there is no sensation of motion, no sign of the journey, just quiet stillness. But beneath that stillness, there is flow, there is direction, there is a hidden structure carrying us along. And as scientists continued to study this region, they began to understand something even more important. Laniakea is not just a structure, it is a pattern of motion, a shared journey, and that raises the next question. If this region is defined by movement, then what does it truly mean to be part of it? When we hear the word structure, we often imagine something solid, a shape with clear edges, something we can point to and say, this is where it begins and this is where it ends. But Laniakea is not like that. It doesn't have walls. It doesn't have a sharp boundary. You can't draw a simple line around it and say, everything inside belongs, everything outside does not. Instead, Laniakea is defined by motion, and that changes everything. Let's take a simple example. Imagine rain falling on a mountain. Some water flows down one side, some flows down another. At the top, there's a point where the direction changes. A drop of water on one side will travel toward one valley. A drop on the other side will travel somewhere else. That invisible dividing line is not something you can see easily, but it exists. And it's defined by the way water moves. Now think of Laniakea in the same way. Galaxies are like those drops of water. They are not fixed. They are moving, and their paths reveal something deeper. Scientists looked at the motion of galaxies and asked a simple question. If we follow their movement backward or forward, where do they seem to be going? And what they found was surprising. There are regions where galaxies all move toward the same general area. Those regions define a kind of boundary. Inside that boundary, galaxies share a common flow. Outside it, they follow a different one. That shared motion is what defines Laniakea. So it's not just a collection of galaxies sitting together. It's a system, a flow, a connected movement. Now here's a question that might come to mind. If Laniakea is defined by motion, does that mean it can change? The answer is yes, in a way. The flow can shift. New structures can form. Gravity can reshape the paths. So Laniakea is not a fixed permanent object. It's part of a dynamic universe, always changing but very slowly. Now let's pause for a moment. Why is this idea so important? Why does it matter that Laniakea is defined by motion? Because it changes how we think about our place in the universe. We are not just located somewhere. We are part of a movement, a shared journey with hundreds of thousands of galaxies. And that journey is shaped by gravity across vast distances. Now imagine being inside a giant river system. You might not see the entire river, you might not know where it begins or ends, but you are part of its flow. Your motion is connected to everything around you. That's what being inside Laniakea is like. Now here's something subtle but fascinating. Even though galaxies are incredibly far apart, their motion is still connected. Not directly, but through the structure of the universe, through the cosmic web, through the influence of dark matter. All of these factors work together, shaping the flow. So Laniakea is not just one thing. It's the result of many influences combined. Now you might wonder, if we are part of this flow, can we see it directly? Can we look up at the sky and notice it? Not really. The motion is too slow, too vast. It happens over millions and billions of years. So from our perspective, everything feels still, but with careful measurement, we can detect it, we can map it, we can understand it. Now here's a common misunderstanding. Some people think that being part of a supercluster means everything is tightly packed together, like a crowded room. But that's not the case. Even within Laniakea, space is mostly empty. Galaxies are separated by huge distances, so it's not a dense structure. It's a connected one, defined by motion, not by closeness. Now imagine a network of roads spread across a country. The cities are far apart. There's a lot of empty land in between, but they are connected by the paths people travel. That's what Laniakea is like, a network defined by movement. Now here's a quiet thought. If our galaxy is part of Laniakea, and Laniakea is defined by motion, then our journey is not random. It is guided, not in a purposeful sense, but in a physical one, shaped by gravity, shaped by structure, shaped by the unseen forces that connect everything. Now let's return to that image of water flowing down a mountain. Each drop follows a path, not because it chooses to, but because of the shape of the land. In the same way, galaxies follow paths shaped by the universe, and we are inside one of those paths. Now here's something to reflect on. Right now, as you feel still, you are part of a flow that stretches across hundreds of millions of light years. A motion so vast, it's almost impossible to picture, and yet, there is no sensation, no sign, just quiet stillness. But beneath that stillness, there is direction, there is movement, there is a shared journey. Now, as scientists continued to study this flow, they noticed something even more striking. Everything inside Laniakea was not just moving together, but slowly drifting toward a particular region, a kind of focal point, a place where the flow seems to lead. And that raises a deeper question. If all of this motion has a direction, then what lies at the center of it? What is everything slowly moving toward? When we think about motion, we often imagine something simple. One object moving from one place to another, a car traveling down a road, a boat crossing a river. But the motion inside Laniakea is not like that. It's not just one object moving. It's everything moving together, hundreds of thousands of galaxies, all drifting in a shared direction, not in perfect lines, not at the same speed, but clearly influenced by the same pull. Now this idea can feel a bit hard to picture, so let's slow it down. Imagine standing on a wide, gentle river. The surface might look calm, maybe a few ripples here and there. If you focus on a single leaf floating on the water, it might spin, wobble, drift slightly to the side. It can feel random, but if you watch long enough, you notice something. Every leaf, no matter how it moves, is slowly being carried in the same direction. That's what's happening inside Laniakea. Each galaxy has its own small motion, local interactions, nearby gravitational pulls. But underneath all of that, there is a larger drift, a shared movement. Now, here's a question that naturally comes up. If everything is drifting together, how fast is this happening? The answer is surprisingly fast, but also incredibly slow, depending on how you look at it. Galaxies can move at hundreds of kilometers per second. That's faster than anything we experience on Earth. But because the distances are so vast, the motion appears gentle, almost still. To give you a sense of that, if you could watch a galaxy move in real time, it would feel like watching the hour hand of a clock. Slow, steady, almost unnoticeable, unless you wait long enough. Now imagine that slow motion happening across millions of light years. That's the drift of Laniakea. Now let's pause for a moment. If all these galaxies are moving together, what is keeping them connected? Why don't they just scatter in different directions? The answer goes back to gravity and structure, the cosmic web, the filaments, the clusters, and the dark matter. All of these create a kind of invisible framework. This framework guides motion. It keeps galaxies following certain paths. So even though each galaxy has its own small movements, the overall direction remains connected. Now imagine a group of people walking through a large field. Each person might take slightly different steps. Some walk faster, some slower, some drift to the side. But if they are all walking downhill, they will naturally move in the same general direction. That's what gravity is doing. It's creating a slope, a gentle pull, guiding everything along. Now here's something interesting. This shared motion is not something we can feel, even though we are part of it. Even though our entire galaxy is drifting along with it. There's no sensation, no sign, just stillness. And that can feel a bit strange, because we often associate motion with feeling. Wind on your face, the vibration of movement, the sound of speed. But in space, there is none of that. Motion happens quietly, smoothly, without resistance. Now here's a question you might be wondering. If everything is drifting together, does that mean we are getting closer to other galaxies? The answer is sometimes yes, sometimes no. Within smaller groups, like our local group of galaxies, some galaxies are moving closer together, like the Milky Way and Andromeda. But on larger scales, the motion is shaped by many influences. Some galaxies move toward dense regions. Others drift apart due to the expansion of space. So it's a balance, a mix of movement shaped by both gravity and expansion. Now let's return to Laniakea. Inside this region, the overall drift points in a similar direction, like water flowing toward a basin, and that basin is where things become even more interesting, because it suggests that there is a region, a kind of center of attraction that is influencing this motion. Now, imagine watching a large crowd from above. Everyone is moving slowly in the same direction. You might not see the destination, but you can tell there is one. Something is drawing them forward. That's what scientists began to notice. This shared drift was not random. It pointed somewhere. Now here's a subtle but important detail. The motion is not perfectly uniform. Not all galaxies move at the same speed. Not all follow identical paths. There are variations, small differences, but the overall direction remains consistent. And that consistency is what reveals the larger pattern. Now here's a quiet realization. We are not separate from this motion, we are inside it. The Earth, the Sun, the entire Milky Way, all drifting together within this vast system. And yet, we feel completely still. Now imagine being on a long, smooth train ride. No bumps, no sudden changes, just steady motion. If you close your eyes, you might feel like you're not moving at all, but outside the landscape is passing by. That's what our situation is like. We are moving, but without any sensation of it. Now here's something to sit with. Every moment of your life has been part of this drift. Every second you have been carried along through space as part of a much larger flow, and yet there is no awareness of it. Just calm, stillness. Now, as scientists followed this shared motion, they traced it further. They asked, if everything inside Laniakea is drifting together, where is it leading? What is at the center of this flow? And that question led to something mysterious, something hidden, something with a gravitational pull strong enough to influence entire regions of galaxies, a place that seems to be drawing everything inward. And that leads to the next question. What is this unseen region that is quietly pulling galaxies across the universe? As scientists followed the motion of galaxies inside Laniakea, they noticed something that stood out. The flow had a direction, not just a general drift, but a clear tendency. Galaxies were slowly moving toward a particular region, and that raised a simple question. What is there? What could be powerful enough to pull entire galaxies across such vast distances? This region was given a name, the Great Attractor. Now, the name itself sounds dramatic, but the idea behind it is actually quite simple. It refers to a region of space with a very strong gravitational pull, a place where a large amount of mass is concentrated, enough to influence the motion of galaxies millions of light years away. Now let's pause for a moment. How strong does something have to be to pull an entire galaxy? Think about Earth's gravity. It can hold you firmly to the ground, but if you jump, you can move against it for a moment. Now think about the Sun. Its gravity holds Earth in orbit, even from 150 million kilometers away. Now imagine something much larger, not just a star, not just a galaxy, but a region containing many galaxies and a huge amount of unseen mass. That's the kind of scale we're dealing with. The Great Attractor is not a single object. It's not like a giant star or a black hole sitting alone in space. It's more like a massive region filled with matter, creating a strong gravitational pull. Now here's something interesting. We didn't discover the Great Attractor by seeing it directly. We discovered it by observing motion. Galaxies were moving in a way that suggested something was pulling them, even though we couldn't see it clearly. It's like watching leaves being pulled toward a drain. In water, you might not see the drain itself, but the movement of the leaves tells you it's there. Now, you might wonder, where exactly is this region? The answer is, in a direction that's difficult for us to observe. It lies behind a dense part of our own galaxy, a region filled with stars, gas, and dust. This area blocks our view like a thick curtain, so even though the Great Attractor is there, we can see it clearly with normal observation. Now imagine trying to look through a foggy window. You know something is outside. You can sense shapes, movement, but the details are hidden. That's what studying the Great Attractor is like. Now here's a question that naturally comes up. If we can't see it well, how do we know it's real? The answer is, in the motion of galaxies. Scientists measure how fast galaxies are moving and in what direction, and when they map that motion, it points toward this region, again and again. From different observations, different angles, the same conclusion appears. There is something there, pulling. Now let's think about scale for a moment. The Great Attractor influences galaxies across hundreds of millions of light years. That's like feeling the pull of something so far away that light takes millions of years just to reach you. To picture that, if you could travel at the speed of light, you would still spend millions of years just getting there. And yet, its gravitational influence reaches across that distance. Now here's something subtle but important. The Great Attractor is not pulling everything in the universe. Its influence is limited to a region, mainly within Laniakea. Beyond that, other structures begin to dominate, other gravitational pulls, other flows, so it's part of a larger system, not the only force, but a major one. Now here's a common misunderstanding. Some people imagine the Great Attractor as something dangerous, like a giant vacuum, pulling everything in uncontrollably, but that's not quite accurate. The motion toward it is very slow, gentle, spread across billions of years. There is no sudden movement, no rapid collapse, just steady drift. Now let's pause and ask something simple. Are we moving toward it right now? The answer is yes. Our galaxy, the Milky Way, is part of this motion. We are slowly drifting in that direction, at a speed of hundreds of kilometers per second. But again, because of the vast distances, this movement feels calm, almost still. Now imagine walking across a very large field. You take a step, then another. From your perspective, the movement feels small, but over time, you cover a great distance. That's what this motion is like. Now here's a quiet realization. Right now, as you sit in stillness, you are part of a journey towards something you cannot see. A region hidden behind the dense parts of our galaxy. A place revealed only through motion. And that can feel a bit mysterious, because it means we are being guided by something we don't fully understand. Now here's a thought that often comes up. What exactly is inside the Great Attractor? Is it just a massive cluster of galaxies? Is it something else? The answer is, we are still learning. There are large structures in that region, clusters, superclusters, and vast amounts of dark matter, all contributing to the pull, but the full picture is still unfolding. Now imagine trying to map a landscape while part of it is hidden behind a mountain. You can infer what's there based on what you see around it, but you can't see it directly. That's where we are with the Great Attractor. Now here's something to sit with. The universe is not just expanding outward, it also has regions of attraction, places where matter gathers, places that shape motion, and the Great Attractor is one of those places. A powerful influence, hidden from view. Now, as scientists continue to study this region, they noticed something even more intriguing. The Great Attractor might not be acting alone. There could be even larger structures beyond it, contributing to the pull. And that raises the next question. If something even bigger lies beyond, then what else is influencing the motion of galaxies? By now, the idea of the Great Attractor begins to feel clear. A massive region, pulling galaxies across vast distances, shaping motion, guiding the flow inside Laniakea. But there's something strange about it. We can't see it clearly, and that leads to a simple, almost curious question. Why? If something is powerful enough to influence entire galaxies, shouldn't it be easy to observe? Shouldn't it stand out, bright and obvious? But the universe doesn't always reveal itself that way. Sometimes, what matters most is hidden. Let's begin with something familiar. Imagine standing in a city at night, surrounded by tall buildings. You try to look beyond them, toward the horizon, but your view is blocked. You know there's more out there. Streets, lights, entire neighborhoods. But the buildings in front of you prevent you from seeing it. Now imagine those buildings stretching for thousands of kilometers. Dense, bright, impossible to see through. That's what our situation is like. The Great Attractor lies in a direction that is hidden behind the dense center of our own galaxy. This region is filled with stars, gas, and dust, so much of it that it blocks our view. Astronomers even have a name for this area. It's often called the zone of avoidance. Not because there's nothing there, but because it's difficult to observe. Now here's a question that might come to mind. What exactly is blocking our view? The answer is interstellar dust and gas. Tiny particles spread throughout the galaxy. They don't seem like much individually, but together they form thick clouds. And these clouds absorb and scatter light, especially visible light. So when we try to look through them, the light from distant objects gets dimmed, distorted, or completely blocked. Now imagine trying to shine a flashlight through heavy fog. The light spreads out. It becomes faint. You can't see what's on the other side clearly. That's what these dust clouds do. Now you might wonder, can't we just use stronger telescopes or different types of light? And the answer is yes, to some extent. Scientists use infrared, radio waves, and X-rays to look through these regions. These types of light can pass through dust more easily, and they have helped us see more than before. But even with these tools, the view is still limited. Details are harder to capture. The picture remains incomplete. Now here's something interesting. Even though we can't see the Great Attractor directly, we can still map its influence by observing how galaxies move around it. It's like standing in a dark room and feeling a gentle pull. You can't see what's causing it, but you can sense its direction. Now let's pause for a moment. If we can't see it clearly, does that make it less real? Not at all. In science, observation isn't just about seeing. It's about measuring effects. Understanding patterns and the motion of galaxies provides strong evidence. Again and again, the data points to the same conclusion. There is a massive region pulling, even if we can't fully observe it. Now here's a common misunderstanding. Some people think that if something is hidden, it must be mysterious in a dramatic or unknown way. But in this case, the mystery is not about something strange or unnatural. It's about limitation. Our position in the galaxy blocks our view. It's like trying to see the back of your own head without a mirror. The information is there, but your perspective limits what you can observe. Now imagine if we could move our viewpoint, if we could travel far above the plane of the Milky Way and look back from a different angle. The region of the Great Attractor might become clearer, the structures more visible, the details easier to map. But for now, we are observing from within, and that creates challenges. Now here's something subtle. The fact that we can't see everything doesn't stop us from understanding. It just means we have to rely on indirect clues. Motion, gravity, light bending. All of these help us piece together the picture. It's like solving a puzzle where some pieces are missing. You don't see the full image, but you can still understand what it shows. Now let's return to something simple. Right now, as you sit here, there are parts of the universe hidden from your view, not just far away, but blocked, obscured. And yet they are still there, still influencing motion, still shaping the flow. Now here's a quiet realization. Our understanding of the universe is always limited by perspective. We see what we can from where we are. And beyond that, there is more. Now imagine being inside a forest. Trees surround you. Your view is limited to what's between them. But above, beyond, the forest continues. You just can't see it all at once. That's what studying the universe feels like. We are inside it, looking outward, trying to understand a structure far larger than our viewpoint allows. Now here's a question to sit with. If something as important as the Great Attractor can remain partially hidden, what else might we be missing? What other structures, flows, or influences lie beyond our view? And that thought leads us forward, because as scientists looked beyond the Great Attractor, they began to notice something even more surprising. There may be even larger structures, even more distant influences, contributing to the motion of galaxies. And that raises the next question. If the Great Attractor is not the only force at work, then what lies beyond it, shaping the universe on an even larger scale? When we talk about the Great Attractor, it's easy to focus on the mystery, the hidden region, the blocked view, the fact that we can see it clearly. But there's another question, just as important. How massive must it be to have such an effect? After all, it's not pulling just a few objects. It's influencing entire galaxies, and not just one or two, but many, spread across enormous distances. So let's slow down and think about that. If something can pull a galaxy, how strong does that pull need to be? Let's start with something familiar. Earth's gravity keeps you grounded. It holds oceans in place. It pulls objects downward, but its influence doesn't stretch very far. If you move far enough away, its pull becomes weak. Now think about the sun. Its gravity reaches much farther. It holds all the planets in orbit. Even distant objects like comets feel its influence. But beyond a certain distance, even the sun's pull fades. Now imagine something far larger. Not a star, not even a single galaxy, but a region filled with many galaxies and a vast amount of dark matter. The combined mass of all of that creates a gravitational pull that extends across millions of light years. To picture this, let's use a simple comparison. Imagine placing a small magnet on a table. It can attract tiny metal objects nearby. Now replace that with a much larger magnet, stronger, heavier. Its pull reaches farther. Now imagine something so large that its influence stretches across an entire room. That's closer to what we are dealing with. But even that falls short, because the Great Attractor's influence extends across distances so large. They are difficult to truly imagine. Now here's something interesting. Scientists estimate that the mass in that region is enormous. Not just the visible galaxies, but also the dark matter surrounding them, all combined, creating a deep gravitational well. Now, what does that mean? A gravitational well is like a valley. The more mass there is, the deeper the valley. Objects nearby tend to move toward the lowest point. So if the Great Attractor has such a strong pull, it means the valley it creates is very deep. Galaxies, like rolling objects, gradually move toward it. Now let's pause for a moment. If this region is so massive, why doesn't everything just rush into it quickly? Why is the motion slow? The answer lies in distance and balance. Even though the mass is huge, the distances are also enormous. So the pull is gentle, steady, acting over long periods of time. It's like a very slight slope. If you place a ball on it, it will roll, but slowly. Now imagine that slope stretching across millions of light years. That's what galaxies experience. Now here's a question that might come to mind. Is the Great Attractor the most massive thing in the universe? The answer is no. There are other massive structures, other clusters, superclusters, and regions filled with dark matter. The universe contains many areas of high mass. The Great Attractor is just one of the most influential in our region. Now here's something subtle. The mass we are talking about is not concentrated in a single point. It's spread out across clusters of galaxies, across large volumes of space. So the pull is not coming from one spot, but from a region. Now imagine standing near a large mountain range. The pull of gravity is not coming from one rock, but from the entire mass of the mountains. That's what creates the effect. Now let's return to motion. Galaxies inside Laniakea are moving at hundreds of kilometers per second. That's fast in human terms. But on cosmic scales, it's part of a slow drift. And that drift tells us something important. It tells us that the mass behind the Great Attractor is strong enough to influence motion, but not so overwhelming that it causes rapid collapse. There is balance. Now here's a common misunderstanding. Some people imagine gravity as something that pulls everything directly inward, in straight lines. But in reality, motion is more complex. Galaxies don't fall straight toward the center. They follow curved paths, influenced by multiple forces, other structures, the expansion of space. So the movement is not simple. It's shaped by many factors. Now imagine multiple gentle slopes overlapping, each one influencing the path slightly. The result is a complex journey. That's what galaxies experience. Now here's a quiet realization. The Great Attractor is not just powerful, it's part of a larger system of forces. Its mass contributes to the flow, but it is not acting alone. And that's important because it means the motion we see is the result of many influences combined. Now let's pause and reflect. Right now, our galaxy is moving, influenced by a region so massive it shapes motion across hundreds of millions of light years. And yet, we feel nothing. No sense of pull, no awareness of direction, just stillness. Now imagine being inside a vast landscape, where the ground slopes gently, so gently, you don't notice it, but over time, you find yourself moving. That's what this is like. Now here's something to sit with. The universe is shaped by mass, by gravity, by structures we can see and structures we cannot. And these forces are guiding motion across unimaginable distances. Now, as scientists studied this region further, they began to ask another question. If the Great Attractor is so massive, is it the only source of this motion? Or is there something even larger, even farther away, also contributing to the pull? And that leads us to the next step, because beyond the Great Attractor, there may be something even more powerful, shaping the movement of galaxies. Now that we understand the pull, the mass, the hidden region we call the Great Attractor, a quiet question begins to form. Is this happening right now? Are we, at this very moment, moving toward it? The answer is simple. Yes, right now, as you sit here, feeling completely still, our galaxy is slowly drifting in that direction, not in a way you can feel, but steadily, continuously, over time. Now let's pause for a moment. What does it actually mean to be falling towards something in space? We usually think of falling as something quick, a drop, a sudden movement downward. But in space, falling is different. It doesn't feel like falling. It looks like motion along a path, a smooth, curved journey shaped by gravity. Remember the moon orbiting Earth. It is constantly falling toward Earth, but at the same time, it moves sideways. So instead of crashing, it circles. That same idea applies on a much larger scale. Galaxies, including our own, are moving along paths shaped by gravity. So when we say we are falling toward the Great Attractor, what we really mean is we are following a path guided by its gravitational pull. Now here's something interesting. The Milky Way is moving toward that region at a speed of about 600 kilometers per second. That's around 2.1 million kilometers per. To make that easier to imagine, at that speed, you could travel around Earth more than 50 times in a single hour, and yet you feel nothing. No motion, no sense of speed, just stillness. Now you might wonder, if we're moving that fast, why doesn't it feel like anything? The answer goes back to something simple. We are moving with everything around us, the Earth, the atmosphere, the entire solar system, all carried along together. It's like being inside a smoothly moving train. If there are no bumps, no sudden changes, you don't feel the motion. Everything feels still. Now let's take that idea and expanded. We are inside a moving galaxy. That galaxy is part of a larger flow, and that flow is guiding us gently toward a region we cannot clearly see. Now here's a question that often comes up. Will we eventually reach the great attractor? The answer is not exactly in the way you might expect. Because the universe is not just pulling things together, it is also expanding. Space itself is stretching. So while gravity pulls galaxies inward, the expansion of space pushes them apart. These two effects work together, sometimes in balance, sometimes with one slightly stronger than the other. So the motion toward the great attractor is not a straight path with a clear endpoint. It's part of a larger, more complex movement. Now imagine walking on a moving walkway at an airport. The walkway carries you forward, but you might also be walking in a certain direction. Your motion becomes a combination of both. That's what's happening on a cosmic scale. Now here's something subtle. The great attractor is not pulling everything directly into a single point. The motion is influenced by other structures too, other massive regions, other flows. So our path is shaped by multiple forces. Now let's pause and think about time. The movement we're talking about happens over billions of years. So even though we are moving fast, the distances are so vast that the change feels slow, almost frozen. To give you a sense of that, if you could watch the Milky Way from far away, its motion would look like the slow movement of a cloud across the sky. Gentle, steady, almost unnoticeable, unless you wait long enough. Now here's a quiet realization. Every moment of your life, you have been moving toward this region, every second, carried along by the motion of the galaxy. And yet, there is no awareness of it, no sign, just stillness. Now imagine standing on a riverbank, watching water flow. You see the movement clearly, but if you were floating in that water, moving at the same speed, it might feel calm, still. That's our situation. We are inside the flow. Now here's a question to sit with. If we are falling towards something, does that mean we are in danger? The answer is no. There is no sudden collapse, no rapid approach. The motion is slow, spread across enormous distances. It's part of the natural structure of the universe, not something harmful, just something vast. Now here's a common misunderstanding. Some people think that being pulled by gravity means we are losing control. But in reality, this motion has always been happening. It's part of how the universe works. It's not new. It's not sudden. It's continuous. Now imagine being on a long journey that started long before you were born, a journey you didn't choose but are part of. That's what this is like. Now let's return to something simple. Right now, as you sit in quiet stillness, you are moving through space at incredible speed toward a region hidden from view, guided by gravity, carried along by the structure of the universe. And yet, everything feels calm. Now here's a final thought to rest on. The idea that we are falling doesn't have to feel dramatic. It can feel gentle, like drifting, like being carried. Because that's what it is, steady movement across an immense cosmic landscape. And as scientists continued to study this motion, they began to measure it more precisely. They asked, how fast is this movement? How strong is this pull? And that leads to the next question. Exactly how fast is our galaxy traveling as it moves through this cosmic flow? If we pause for a moment and think about everything we've explored so far, a quiet realization begins to settle in. We are moving, not just a little, not just slowly, but at a speed that is almost impossible to imagine. And that raises a simple question. How fast are we really going? Let's start with something familiar. A car on a highway might travel at around 100 kilometers per hour. At that speed, you can cross a large city in less than an hour. It feels fast. You can feel the motion. You can see the world passing by. Now imagine something faster. An airplane. It travels at around 800 to 900 kilometers per hour. At that speed, you can cross entire countries in just a few hours. Now take that idea and multiply it again. Our planet, Earth, moves around the Sun at about 107,000 kilometers per hour. Already, that's far beyond anything we experience directly, but we don't feel it, because everything around us is moving together. Now, let's go even further. The Sun itself, carrying the entire solar system, moves around the center of the Milky Way at about 828,000 kilometers per hour. That's fast enough to circle Earth more than 20 times in a single hour. And still, we feel nothing. Now here's where it becomes even more astonishing. The Milky Way itself, our entire galaxy, is moving through space at about 600 kilometers per second. That's around 2.1 million kilometers per hour. To picture that, if you could travel at that speed on Earth, you could go around the entire planet more than 50 times in just 1 hour. And yet, there is no sensation of motion, no wind, no vibration, no sound, just stillness. Now let's pause and ask something simple. Why don't we feel this speed? The answer is, because speed alone doesn't create sensation. It's change in speed, acceleration, that we feel. If something moves at a constant speed, smoothly, without sudden changes, it feels still, like sitting in a train that glides quietly along the tracks. If you close your eyes, you might not even notice you're moving. That's what our situation is like. Now here's a question that often comes up. If we are moving this fast, why don't the stars look like they're rushing past us? Why does the sky look calm? The answer goes back to distance. The stars we see are incredibly far away. Even the closest ones are separated by huge distances. So even though we are moving quickly, the change in our position relative to those stars is very small from moment to moment. It's like watching a distant mountain while driving. Even at high speed, the mountain seems almost still. Now imagine that mountain millions of times farther away. That's what the stars are like. Now let's think about this in another way. If you were inside a plane flying above the clouds and you looked out the window, the clouds might appear to drift slowly, even though you're moving very fast. But if you were closer to the ground, you would see things moving much faster. In space, everything is very far apart, so motion appears gentle. Now here's something interesting. Our galaxy's speed is not fixed in a simple way. It is influenced by many factors. The pull of the Great Attractor, the influence of other massive structures, the expansion of the universe. So our motion is part of a complex system. Not just a straight path, but a combination of movements. Now imagine being in a flowing river, while also walking sideways, and the ground beneath you is shifting slightly. Your path becomes a blend of all these motions. That's what our movement through space is like. Now let's pause for a moment. If we are moving this fast, what does that mean for our journey? It means that every second, we are traveling an enormous distance. In just 1 second, at 600 kilometers per second, we move 600 kilometers. That's like traveling from one city to another in the blink of an eye. Now imagine that happening every second, continuously. Now here's a quiet realization. Every moment of your life, you have been traveling through space at incredible speed, faster than anything humans have ever built. And yet, you feel completely still. Now here's a question to sit with. If we could suddenly stop, If all this motion disappeared, what would it feel like? The answer is, we can't really know, because everything we experience is already part of this motion. There is no reference point outside of it. We are inside the system. Now here's a common misunderstanding. Some people think that speed alone makes something dramatic, but in the universe, even extreme speeds can feel calm, because of scale, because of distance, because of smooth motion. Now imagine drifting in a vast ocean. Even if the current is strong, if it's steady, you might not feel it. That's what this is like. Now let's return to something simple. Right now, you are moving faster than any car, any plane, any spacecraft, carried by Earth, carried by the sun, carried by the galaxy, all layered together. And yet, there is no sensation, only stillness. Now here's something to reflect on. Speed in the universe is not about rushing. It's about motion across vast distances, gentle, steady, continuous. And as scientists measured this speed more carefully, they began to notice something even more intriguing. The motion we see cannot be explained by a single source alone. There are multiple influences, multiple structures, each contributing to the movement, and that leads to the next question. If the Great Attractor is not the only force, then what other massive structures are shaping the path we are following? As scientists continued to trace the motion of galaxies, something unexpected began to appear. The Great Attractor, powerful as it is, might not be the whole story. There seemed to be something beyond it, something even larger, even more distant, also influencing the flow. This structure is known as the Shapley supercluster, and when you begin to understand its scale, it changes how you see everything. Let's start with something simple. Imagine standing in a wide valley. You feel a gentle slope beneath your feet, guiding you in one direction. At first, you might think that slope is caused by a nearby hill, but as you look farther, you realize there's an even larger mountain in the distance. Its pull, its shape, influences the land more than you first thought. That's what scientists began to notice. The motion of galaxies, especially at very large scales, could not be explained by the Great Attractor alone. There had to be something more, something farther away, adding to the pull. Now, what exactly is the Shapley supercluster? It's one of the most massive structures in the nearby universe. A vast region filled with many galaxy clusters, all packed together. If a single galaxy cluster is like a city, then the Shapley supercluster is like a dense region filled with many cities, all close to each other. Now let's pause for a moment. How big is this structure? The Shapley supercluster spans hundreds of millions of light years. It contains dozens of large galaxy clusters and thousands of individual galaxies. To picture that, if each galaxy were a grain of sand, this structure would be like a massive stretch of shoreline filled with countless grains. Now imagine the combined mass of all those galaxies, plus the dark matter surrounding them. The gravitational pull becomes enormous. Now here's something interesting. The Shapley supercluster lies beyond the Great Attractor, farther away, deeper in the same general direction. So when scientists mapped the motion of galaxies, they noticed that the flow didn't just stop at the Great Attractor. It continued, as if the pull extended even farther. Now this raises an important question. Is the Great Attractor the main cause of the motion, or is it just part of a larger system? The answer seems to be it's part of something bigger. The Great Attractor contributes to the pull, but the Shapley supercluster, with its immense mass, may be adding even more influence. Now imagine being in a river. At first you feel the current pulling you. You might think it's caused by a nearby bend, but farther downstream, there's a much larger drop, shaping the flow more strongly. That's what this situation is like. multiple influences working together. Now here's a question that might come to mind. If the Shapley supercluster is so far away, can it really affect us? The answer is yes. Because gravity doesn't stop at short distances, it extends across space. Even though the pull becomes weaker with distance, when the mass is large enough, its influence can still be significant. Now let's think about scale again. The distances involved are enormous. Light takes hundreds of millions of years to travel across these regions. So the motion we see is the result of forces acting over incredibly long periods of time. Now here's something subtle. The motion of our galaxy is not pointing directly at one single object. It's the result of combined pulls. The Great Attractor, the Shapley supercluster, other surrounding structures, all contributing to the direction. Now imagine standing in a wide open field with several hills around you. Each one pulls slightly, guiding your path. Your movement becomes a balance of all those influences. That's what galaxies experience. Now here's a common misunderstanding. Some people imagine space as having a single center, place where everything is moving toward. But that's not how the universe works. There is no single center. Instead, there are many regions of mass, many areas of influence, and motion is shaped by all of them together. Now let's return to something simple. Right now, our galaxy is moving, not just because of one structure, but because of many. The Great Attractor pulls. The Shapley supercluster adds to that pull, and other structures also play a role, all combined, creating the path we follow. Now here's a quiet realization. The universe is not guided by a single force. It's shaped by a network of influences, a balance of pulls across vast distances, and we are inside that system, moving along with it. Now imagine being part of a large crowd, where movement is shaped not by one person, but by the flow of everyone together. That's what this is like. Now here's something to reflect on. Even though we can map these structures, even though we can measure their influence, there is still much we don't fully understand. The exact balance of forces, the full extent of these structures, the deeper connections between them. Now here's a question to sit with. If our motion is shaped by multiple massive regions, how do these influences combine? How do they interact to create the flow we observe? And that leads us to the next step. Because the movement of galaxies is not caused by a single pull, but by many working together. And understanding that brings us closer to seeing the full picture of how everything is moving. By now, a quiet pattern has started to emerge. The motion of galaxies, including our own, is not caused by just one thing. Not a single force, not a single destination, but by many influences, all working together. And that changes how we understand this journey. Because instead of being pulled to one point, we are moving through a landscape shaped by many. Let's slow this down and picture something simple. Imagine standing in a wide open field. Around you, there are several hills. Each one has its own slope. If you begin to walk, your path won't be guided by just one hill. It will be shaped by all of them. You might drift slightly toward one, while also being influenced by another. Your movement becomes a blend. That's what galaxies experience. The Great Attractor pulls. The Shapley supercluster adds to that pull. Other clusters, filaments, and regions of dark matter all contribute. Now here's a question that naturally comes up. If there are multiple pulls, how do they combine? Do they cancel each other out? Or do they create something more complex? The answer is, they combine. Each force adds its influence, and the result is a direction, shaped by all of them together. It's like being in water with several gentle currents. Each current pushes slightly, but the overall movement is the sum of all those pushes. Now let's pause for a moment. Why is this important? Because it shows that the universe is not simple, not in the sense of one cause, one effect. Instead, it's a system, a network of interactions, where many forces shape motion at the same time. Now imagine a group of people walking together. No one is giving orders. No single person is leading. But the crowd still moves as a whole, guided by subtle influences. That's what cosmic motion feels like. Now here's something interesting. These influences don't all act equally. Some regions are more massive. Some are closer, so their pull is stronger. Others are farther away, or less massive, so their effect is weaker. But even weak influences can matter over time. Remember earlier, a gentle push, applied for long enough, can move something far. The same is true here. Now here's a question you might be wondering. If multiple structures are pulling, can the direction of motion change? The answer is yes, but very slowly. As the universe evolves, as structures grow, merge, or shift, the balance of forces can change, and that can slightly alter the paths galaxies follow. But these changes happen over incredibly long timescales, millions, even billions of years. So from our perspective, the motion feels steady. Now let's think about this in another way. Imagine a boat floating on a calm sea. There are several gentle currents beneath it. At first, the movement seems random, but over time, the boat follows a path shaped by all those currents combined. That's what galaxies are doing. Now here's a subtle but important idea. There is no single center pulling everything. No fixed point where all motion leads. Instead, there are regions of influence, areas where gravity shapes motion in different ways, and galaxies move through this network, responding to those influences. Now here's a common misunderstanding. Some people imagine the universe as having a central point, like the center of a circle, but the universe doesn't work like that. It has no single center. It expands in all directions, and within that expansion, gravity creates local structures, local flows. So motion is not about heading toward one place, but about following the shape of the universe. Now let's return to something simple. Right now, our galaxy is moving because of the combined pull of many structures: the Great Attractor, the Shapley supercluster, other nearby clusters and filaments, all contributing, all shaping the path. Now here's a quiet realization. We are part of a system where motion is not simple, but layered, not direct, but guided, not controlled by one force, but by many. And yet, it all feels calm, still, almost motionless. Now, imagine standing on a gently sloping landscape, with hills all around. You don't feel the slope strongly, but as you walk, your path slowly curves. That's what this is like. Now here's something to reflect on. Every moment, you are moving through space, following a path shaped by countless influences, forces acting across distances so vast, they are hard to imagine, and yet, there is no awareness of it. Now here's a question to sit with. If motion is shaped by multiple structures, how does that fit into the larger picture of the universe? Because there's something else happening at the same time. Something that might seem to go in the opposite direction. The universe itself is expanding. Space is stretching outward. So while gravity pulls things together, expansion pushes them apart. And that creates a balance, a tension between two forces. And that leads to the next question. How does this balance work? Why doesn't everything collapse or drift endlessly apart? Up to this point, everything has been pointing in one direction. Gravity pulling, galaxies drifting toward massive regions, flows forming across the universe, But there's another part of the story, just as important. The universe is expanding, and that might sound like it goes against everything we've been talking about. If gravity pulls things together, why is the universe spreading out? How can both of these be true at the same time? Let's slow down and take it step by step. First, what does it mean for the universe to expand? It doesn't mean galaxies are flying outward into empty space. It means space itself is stretching. The distances between galaxies, especially those far apart, are increasing over time. Now here's a simple way to picture it. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move away from each other, not because they're moving on their own, but because the surface itself is expanding. That's similar to what's happening in the universe. Now let's pause for a moment. If everything is expanding, does that mean all galaxies are moving away from each other? The answer is not always. And this is where things get interesting. Gravity still works. It still pulls objects together. So in regions where gravity is strong, it can overcome the expansion. Now imagine stretching a rubber sheet while also placing small weights on it. The sheet expands, but the weights still pull nearby objects toward them. That's what's happening in space. On very large scales, expansion dominates. Galaxies far apart drift away from each other, but on smaller scales, gravity takes over. Galaxies within clusters remain bound. Groups of galaxies stay together. Now here's a question that often comes up. Why doesn't it tear galaxies, or even solar systems, away? The answer is strength. Gravity within galaxies is strong enough to hold them together. The expansion of space is very gentle at those smaller scales, so it doesn't break those bonds. To picture that, imagine holding two objects with a strong grip. If something gently pulls them apart, your grip keeps them together. That's what gravity does. Now let's think about scale again. At distances of millions of light years, gravity becomes weaker and expansion becomes more noticeable. So galaxies far apart drift away from each other over time. Now here's something subtle. The expansion of the universe is not slowing down, it's actually speeding up. This is due to something called dark energy. We'll talk more about that soon. But for now, it's enough to understand that space is stretching faster over time. Now let's pause and bring this back to our main idea. We have two forces at work: gravity pulling matter together, expansion pushing space outward, and these two are constantly interacting. Now imagine a tug of war. On one side, gravity, on the other, expansion. But instead of a sudden pull, it's a slow, steady balance. In some regions, gravity wins. In others, expansion takes over. Now here's a question to sit with. Where do we fit in this balance? Our galaxy, the Milky Way, is part of a group of galaxies. This group is held together by gravity. So within this group, expansion does not pull us apart. We remain connected. But beyond that, at larger distances, expansion becomes more noticeable. Now imagine standing in a crowd. The people near you stay close, but those far away slowly drift apart. That's what this is like. Now here's something interesting. Even though the universe is expanding, we are still moving toward the great attractor, because gravity in our region is strong enough to shape that motion. So both things are happening at the same time. We are being pulled while space itself is stretching. Now this might feel a bit confusing at first. How can something move toward a point while everything is expanding? The answer is because these effects happen at different scales. Gravity dominates locally. Expansion dominates at larger distances. Now imagine walking on a moving walkway. The walkway carries you forward, but you can still walk in your own direction. Your motion becomes a combination of both. That's what galaxies experience. Now here's a common misunderstanding. Some people think the expansion of the universe means everything is flying apart rapidly, but it's much more gentle than that. Especially on smaller scales, it's a slow stretching, not a violent tearing. Now let's return to something simple. Right now you are part of a system where two forces are always at work. Gravity pulling inward, expansion pushing outward, and your motion is shaped by both. Now here's a quiet realization. The universe is not just collapsing and not just expanding. It's doing both at the same time, in different ways. Now imagine breathing. Inhale, exhale. Expansion, contraction. A balance between two movements. That's what the universe feels like. Now here's something to reflect on. Even though these forces are immense, they act gently, over vast distances, over long periods of time, and that's why everything feels calm. Now here's a question that naturally follows. If expansion is speeding up, why doesn't it completely overcome gravity? Why doesn't everything drift apart forever? And that leads us to the next step, because there is something else, something even more mysterious, driving this expansion, and understanding it brings us closer to the full picture of what is shaping the universe. When we think about gravity, it feels powerful. It holds us to the ground. It keeps planets in orbit. It pulls galaxies together. So it's natural to wonder, if gravity is always pulling, why hasn't everything already collapsed? Why isn't the entire universe just one massive dense point? Why are there still vast spaces, flowing motion, and expanding distances? The answer lies in something that feels almost opposite to gravity, something that pushes outward, something we call dark energy. Now that name might sound a bit mysterious, but the idea can be understood in a simple way. Dark energy is not something we can see, not something we can touch, but we can observe its effect, and that effect is expansion. Let's go back to something familiar. Imagine you're stretching a rubber band. You pull your hands apart, and the band stretches. Now imagine that instead of slowing down, the stretching begins to speed up on its own. Your hands don't even need to pull harder. It just keeps expanding, faster over time. That's what's happening in the universe. Space itself is stretching, and that stretching is accelerating. Now let's pause for a moment. If gravity pulls things together, and dark energy pushes space apart, then the universe is in a kind of balance. A quiet tension between two forces. Now here's a question that often comes up. Which one is stronger? The answer depends on the scale. At small scales, gravity wins. It keeps galaxies together. It holds solar systems in place. It shapes clusters. But at very large scales, dark energy becomes more dominant. It pushes galaxies farther apart. It stretches the fabric of space itself. Now imagine a group of people holding hands in a circle. Their grip represents gravity. Now imagine the ground beneath them, slowly expanding. At first, their grip keeps them together. But if the ground keeps stretching, eventually, the distance between groups increases. That's what's happening in the universe. Now here's something important. Dark energy doesn't pull or push in the way we're used to thinking. It doesn't act like a force between objects. Instead, it's a property of space itself. As space expands, dark energy causes that expansion to accelerate. Now that might feel a bit abstract, so let's simplify it. Imagine drawing dots on a balloon again. As the balloon inflates, the dots move apart. But now imagine that the balloon starts inflating faster on its own. That's closer to what dark energy does. Now here's a question to sit with. If dark energy is pushing everything apart, why doesn't it tear galaxies apart? Why doesn't it pull planets away from stars? The answer is, scale and strength. Gravity within galaxies is strong enough to hold them together. Dark energy is very gentle at those smaller scales, so it doesn't break those bonds. To picture that, imagine holding a small object tightly in your hand while standing in a slowly expanding room. The room grows, but your grip keeps the object secure. That's what gravity does. Now let's return to the bigger picture. The universe is not collapsing because dark energy is pushing outward. It balances gravity on the largest scales. And in fact, it's doing more than balancing. It's slowly winning. The expansion of the universe is speeding up. Now here's something that often surprises people. Dark energy makes up most of the universe. More than visible matter, more than dark matter. It's the largest part of the cosmic balance. And yet, we don't fully understand what it is. We know its effect. We can measure it. But its true nature remains one of the biggest mysteries in science. Now let's pause for a moment. If dark energy is so dominant, does that mean gravity will eventually lose? Will everything drift apart forever? The answer is, that's one possibility over extremely long timescales. Galaxies far apart may continue to move away from each other. Clusters may become isolated. The universe may grow colder, more spread out, but within local regions, gravity will still hold things together. So it's not a complete separation. It's a gradual stretching. Now imagine a loaf of bread rising in an oven. The dough expands, but small clusters of raisins inside stay grouped together. That's what this is like. Now here's a quiet realization. The universe is shaped by balance, not by one force alone, but by the interaction of many. Gravity pulls, dark energy expands, and together they create the structure we see. Now let's bring this back to something simple. Right now, as you sit in stillness, you are part of this balance, held together by gravity, carried along by cosmic flow, and surrounded by a universe that is slowly expanding, all happening at once. Now here's something to reflect on. The universe is not rushing toward collapse, nor is it flying apart in chaos. It is evolving, gently, steadily, over immense stretches of time. Now here's a question that naturally follows. If this balance continues, what will happen in the future? How will this motion, this flow, this expansion, shape what the universe becomes? And that leads us to the next step, because the journey we are part of does not stop here. Far into the future, in ways that are both quiet and profound. If we gently follow this motion forward, beyond the present, beyond what we can directly observe, a quiet question begins to form. Where is all of this going? If galaxies are drifting, if space is expanding, if gravity and dark energy are shaping everything, what will the universe look like in the future? Let's take this slowly. Right now, galaxies move along filaments. They gather in clusters. They drift toward regions like the Great Attractor. All of this happens gradually, over billions of years. So what happens if we let time continue? The first thing to understand is this. Local structures will become more connected. Galaxies that are already close will continue to influence each other. Some will merge. Others will orbit together. Over time, smaller groups can combine into larger ones. Now imagine two clouds drifting toward each other. At first, they are separate, but slowly, gently, they begin to overlap, blend, become one. That's what galaxy mergers are like. Not sudden collisions, but slow interactions, stretching across millions of years. Now here's something interesting. Our own galaxy, the Milky Way, is expected to merge with the Andromeda Galaxy. This will happen in about 4 to 5 billion years. That might sound like a long time, and it is, if all of human history were compressed into a single day. This event would happen thousands of years into the future. Now you might wonder, will this be violent? Will stars crash into each other? The answer is, not really. Space is so empty that even during a merger, most stars pass by each other without direct contact. It's more like two clouds blending than two solid objects colliding. Now let's pause for a moment. If galaxies merge, what happens to the structure of the universe? Over time, clusters can become more massive, galaxies within them can combine. But at the same time, the expansion of the universe continues. And this is where things become even more interesting. On very large scales, galaxies that are far apart will continue to drift away from each other. Because of dark energy, that expansion is accelerating. So while local groups become more connected, distant regions become more separated. Now imagine a gathering of people. Small groups come closer together, but the overall crowd slowly spreads out. That's what the universe is doing. Now here's a question that often comes up. Will everything eventually come together or drift apart forever? The answer depends on scale again. Within local regions, gravity keeps things connected. Galaxies merge, clusters grow, but beyond those regions, expansion dominates. So distant galaxies move farther away. Eventually they may become so distant that their light can no longer reach us. Now let's think about that for a moment. Right now, when we look into space, we can see distant galaxies. Their light travels for millions or billions of years before reaching us, but in the far future, some of those galaxies will move so far away that their light will never reach us again. They will fade from view, not because they disappear, but because space between us grows too large. Now imagine standing on a shore, watching ships sail away. At first you can see them clearly, then they become smaller, fainter, until eventually they vanish beyond the horizon. That's what will happen to distant galaxies. Now here's a quiet realization. The universe of the future may look very different from what we see today. Observers in the distant future might see far fewer galaxies because many will have moved beyond visibility. Now let's return to motion. Even as galaxies drift apart on large scales, local motion continues. Galaxies within clusters will keep interacting, merging, evolving. So the universe doesn't stop moving. It continues in a quieter, more spread out way. Now here's something subtle. The cosmic flow we experience today will also evolve. As structures change, as mass redistributes, the paths galaxies follow can shift slightly, but always slowly, always gently. Now imagine a river changing its course over time, not suddenly, but gradually. That's what cosmic motion is like. Now let's pause and reflect. Right now, we are part of a universe that is dynamic, changing, moving, but in the future, that motion may feel quieter, more stretched out, more isolated. Now here's a question to sit with. What does that mean for our place in the universe? It means we are living at a time when the universe is still rich with visible structure, when galaxies are still within view, when motion is still connected across vast regions. And that makes this moment special. Now here's a quiet thought. Every moment, you are part of a journey that stretches billions of years into the future, a motion that will continue long after everything we know has changed. And yet, right now, it feels still. Now imagine standing at the edge of a long path. You can only see a small part of it, but you know it continues far beyond your view. That's what the future of the universe is like. Now here's something to reflect on. The motion we are part of does not end. It transforms, it evolves, it continues, and that leads us to one final thought. Because when you step back and take in everything we've explored, a deeper realization begins to form. We are not standing still. We have never been still, and we never will be. And that brings us to the final question. What does it truly mean to be part of this vast, unstoppable flow? When you step back and gently take in everything we've explored, a quiet realization begins to form. It doesn't come all at once. It settles slowly, like a thought that keeps returning, becoming clearer each time. We are not still. We have never been still. And we are not in control of this motion right now. As you sit here, it feels like you are resting, not moving, grounded. But beneath that feeling, there is motion layered upon motion. The Earth is turning. The Earth is orbiting the Sun. The Sun is moving through the Milky Way. The Milky Way is drifting through space. And all of it is part of a larger flow, a movement shaped by gravity, by structure, by forces we cannot see. Now let's pause for a moment. If everything is moving, why does it feel so calm? Why does it feel like stillness? The answer is simple. Because we are inside the motion. We move with it. There is no outside reference point, nothing to compare it to, so it feels like nothing is happening. Like being inside a smoothly moving train with no windows. You don't feel the speed, you don't see the motion, you just sit in quiet stillness. Now imagine that train is not just moving across land, but through an endless landscape, with no edges. That's what this is like. Now here's a question that naturally comes up. If we are moving and being pulled, does that mean we are heading somewhere we can't escape? In a way, yes, we are part of a system, a flow, guided by gravity, shaped by structures like the Great Attractor and beyond. But this is not something sudden, not something we can feel. It's not a fall in the way we imagine falling. It's more like drifting. Now imagine floating in a vast ocean. There is a current beneath you. It carries you gently, steadily, in a direction. You don't fight it. You don't feel resistance. You simply move with it. That's what our motion is like. Now here's something that can feel a little unsettling. We are not choosing this direction. We are not controlling this movement. We are part of it. And that can feel strange, because we are used to thinking of ourselves as still, as grounded, as separate from the larger universe. But the truth is, we are deeply connected to it. Now let's pause and reflect on something simple. Every second, you are traveling through space at incredible speed, hundreds of kilometers every second, thousands of kilometers in just a few moments, and yet you feel nothing. Now imagine if you could suddenly step outside of this motion. If you could see your path through space, it would not be a straight line. It would be a long, spiraling, flowing path, stretching across the galaxy, across the universe. Now here's a quiet realization. Your entire life, every moment, has been part of this journey. You have never been in the same place twice, not even for a second. Now here's a question to sit with. If we are always moving, what does here really mean? The place you are in right now is not fixed. It is part of a path, a moment along a journey. Now imagine drawing a dot in space to mark where you are. A second later, you are somewhere else. A minute later, farther still. Now extend that over years, decades. Your path becomes something vast, something continuous. Now here's something to reflect on. We often think of ourselves as observers of the universe, looking out at it, studying it, but in reality, we are part of it, moving with it, shaped by it. Now here's a common misunderstanding. Some people imagine the universe as something out there, something separate from us. But the truth is, there is no separation. We are inside it. Now let's return to that feeling of stillness. It's comforting, quiet, calm, but beneath it, there is motion, endless motion. Now imagine sitting in a quiet room while outside an entire city is moving. Cars, people, lights, all in motion. You don't hear it, you don't feel it, but it's happening. That's what this is like. Now here's a final thought to rest on. The realization that we are part of an unstoppable flow doesn't have to feel frightening. It can feel peaceful, because the motion is gentle, steady, reliable. It has always been there. Now imagine being carried along a calm river. You don't resist it, you don't fear it. You simply move with it. Now here's something to sit with, quietly. Right now you are moving through space, through a vast, structured universe, guided by forces that stretch across unimaginable distances. And yet, you feel completely still, and maybe that is the most surprising thing of all, that something so vast, so constant, can feel like nothing at all.